Hi, everybody, and welcome to PyHEP on Friday. People are still joining, so I think we're going to wait a couple of minutes more and just let everyone get settled into the meeting before we get started. So just a few minutes and we'll get going. Hi, everyone. So for those of you who've just joined, there are still many people coming in, so I think we'll wait just a few seconds more and then get started at 3 minutes past. If that's okay with you, Doug?
Yep, sounds fine.
Okay, great. I can hear you very well.
Wonderful.
That's good too. Fantastic. Okay, so let's begin. So welcome everyone to the Friday of PyHEP 2022, our last day, unfortunately, but we still have many good things to come. And we'll be kicking off today with a tutorial on Dask, which has become really one of the go-to packages actually for PEP in the last couple of years. Really nice to see that happening. And we have Doug here who's going to give us the tutorial over the course of the next hour. And I will post the Slido link in the chat just to remind people of where you can ask questions for Doug. And I think with that, I can say, take it away, Doug.
Awesome. Yeah, thank you very much. Yeah, good morning. Morning for me here in Austin, Texas. Good afternoon, evening, wherever you are. Yeah, so I will be talking for the next 45, 50 minutes about Dask. The talk is going to serve three purposes, really. One, just to be kind of an introduction, a high-level overview of Dask. Two, to introduce some new libraries that we've been working on, collaborating with scikit-hep folks to plug Dask a little bit more into scikit-hep packages. And three, as a little bit of an appetizer for a couple of presentations that will be following, that will follow up this tutorial. So yeah, we'll go ahead and get started. Kind of the first little bit of the notebook is just almost like a slide here. So Dask is a pure Python library for parallel computing and distributed computing, really to scale up the PyData ecosystem. So I know Dask has been mentioned at least a couple of times here during PyHEP, but kind of starting from square one here, just really starting as if everyone has no knowledge of Dask. We have Dask broken into two main components. There's the collections library or libraries, depending on how you like to see it. Sometimes this is referred to as Dask core. And listed here, there's the Dask array library, the Dask bag library, Dask data frame, and Dask delayed. So these all serve a purpose of partitioning or chunking existing Python workflows such that they can be distributed. So in Dask array's case, this is partitioning or chunking NumPy. And Dask bag, this is just regular Python objects, anything that can be iterated on in Python. Dask data frame, this maps to pandas workflows, and Dask delayed is meant for parallelizing any kind of any Python workflow that you can dream up that perhaps doesn't fit into one of the PyData libraries. So Dask itself is a PyData library, but really what it's doing is it is just scaling up the existing PyData libraries. Secondary to the collections libraries are the execution engines. So what Dask does is it builds task graphs, and we'll talk a little bit more about that. And once the task graph has been created with one of the collection APIs, then it needs to be executed, and it gets executed by a scheduler. So there are a number of schedulers. When you just spin up Dask for the first time on a laptop, you get the threaded scheduler usually. So this is just some Dask will take advantage of all the threads on your machine. But then there's also the dedicated distributed project, which is sometimes called Dask distributed. And this is for scaling up on perhaps a cluster that is available to you, some HPC system, or perhaps the cloud. So those are the two main components of Dask. There's the library to create task graphs, the collections libraries, and then there's the execution engines. So this graphic here really kind of shows that, illustrates this in a single picture where there is an API, the collections API for creating task graphs that get passed to a scheduler for execution. So that is the very high level view of the Dask project, the Dask ecosystem, really. It's not just a single project. And so, yeah, I mentioned here, there are a number of other projects in the ecosystem leveraging both of these components, and we'll be talking a little bit more about that later too. So I'll start off with the first example here using Dask delayed. So Dask delayed is the collection library that really allows you to turn any Python workflow into a task graph. So I'm defining a function here called just increment the argument. So it takes in x, it returns x plus 1. And then I'm just turning this function into a delayed version of the same function. So if I do this and I pass in 7 to inc, I'm not actually going to get 8. I'm going to get a delayed object. So I can assign this now to a variable called 8. And to actually get a result, you have to say compute. You're telling Dask, compute this thing. So I get the answer 8. This is one of the things about Dask that I remember when I first started using it. It took me it took me a little while to wrap my brain around it. And that is that Dask objects are just some staged thing. It's lazily evaluated. So when you're doing things with a Dask API, until you actually call compute, you're just staging up something to happen. Everything is lazy. So taking this a step further, we can chain together delayed calls. So here I'm using the decorator syntax. So now I'm having my increment function and combining this with an add function. So I can say increment 1 and increment 2, and then add those together. So of course, 1 plus 1, 2, 2 plus 1, 3. This will be 5. Didn't execute that cell. There we go. So now one of the powerful things about delayed is you can pass delayed objects into other functions that are that have been decorated as a delayed, as a Dask delayed object. So one of the really cool things about Dask, and especially using Dask in like a Jupyter notebook, for example, like this workflow here, is there are a lot of diagnostics and tools to actually see what's going on. But before we look at that, I'm going to bear with me while I spend just a quick second on a little bit lower level than what is typical, what would be typical diagnostics, and that is what some details about exactly how Dask represents the task graph. So I'm going to take this task graph of adding 2 and 3, and I'm going to call the Dask property and convert that to a dictionary. The Dask property on a Dask collection is the task graph. And so the way that Dask actually stores this information, the task graph, is in just a plain Python dictionary. So what Dask is doing is it's creating something kind of Lispy. Every task has a label and then some function, some lazy function call represented by a tuple. And the way that Dask can chain these together is that the label assigned to a task can be passed into a later task. So starting with the 2 increment functions, I have my increment of 2. So the first element in the tuple is a callable. In this case, it's my function increment. And then the later arguments are the arguments to be passed to that function. Same thing with incrementing 1. But then you'll notice that the increment steps are then the arguments in the add step. So this is a very, very low level view of Dask, but it's to me, I think it's a very useful thing to have in mind as to exactly how Dask is executing is accomplishing the task of building a task graph and then executing it. So when Dask goes to compute this, the final thing it wants to do is the add function, but it will see when it comes into the add function that it needs to compute the increment steps first. So then it'll walk down the graph and it'll compute these steps in order to accomplish the complete task graph. Like I said, this is a very low level view. It's not the easiest thing to parse. There's a much better way of inspection, and Dask has a visualized method on the collections so that one can actually look at a picture of the graph. So we see obviously that there are 2 increment calls going into an add, and then the circles are function calls and the squares are data resulting from those steps in the task graph. So that's the most verbose example I'll give today, but it really is a core example of it really surrounds the full Dask landscape and what's getting accomplished. Okay, so now moving on to something that is a little bit more targeted to perhaps a workflow that folks here at PyHEP might be interested in. So here in the second example, we'll still use delayed here one more time. We'll look at something that is loading a file, doing something with the contents that you've loaded, and then histogramming that calculation. So we'll leverage Dask, and then we'll compare this to not using Dask. So I've got a few imports here just from the ecosystem here, uproot, awkward, hist, and I'm also just borrowing a file from scikit-hep's test data. So I just have one root file that I'm just copying 4 times for kind of the example purposes here. So the 3 steps, really 4, but the last 2 are very similar. We're going to read in some tree with uproot, and I added a little time sleep 1 second here to fake making the file larger. We're going to do some calculation by passing in the tree, and that calculation is just going to be taking the absolute value of the differences in energies and the particles in this file. Then we're going to histogram that value by taking in some data and defining a bin, the binning. And then finally, because we are doing this over multiple files, we're going to aggregate by just summing those histograms. So these are the 4 steps. Doing this in a loop here. So recall that I'm just taking a file here and repeating it 4 times. So I have 4 paths here. So I'm going to do the read tree step, then I'm going to do the calculation, and then I'm going to create the histogram. I'm going to add those histograms to a list, which I'm then going to pass into the delayed sum. So I'll go ahead and execute these cells before I talk a little bit more. I'm going to do the same thing without Dask so it can just run in the background, and we'll scroll back up. Okay, so as I was saying, we have our steps. The final result of after our loop here is just to have a list of delayed objects that I passed into the final aggregation function. And I'm going to go ahead and visualize this. So we have now our read tree step, the calculation, the histogram on each file, and finally combining everything in the final step. So this is obviously a small workflow here, but it's very representative of something that is quite common in Dask for folks that are just getting started and trying to scale up, their specific workflow. Plugging into delayed is, kind of a first step to take something that perhaps isn't just operating on arrays or just operating on data frames. It's a first step to plug into the Dask ecosystem, to just start delaying an existing workflow. So what I did here is I went ahead and timed this. So recall I had 4 files, and each file, when reading, I added that little sleep step to kind of fake it being a larger file. The total time to execute the full calculation was 1.18 seconds on my laptop. And even though with 4 files, we waited 1 second per file, I mean, this is a representation of Dask being parallelized. So Dask executed all of those read steps in parallel, each one, adding that additional unnecessary 1 second. So if we compare this to the serial, this is the exact same setup here, but this time without Dask, of course, it took over 4 seconds, because in this loop, each time we read the tree, it took that sleep of 1 second. So I wanted to show that just as an example of Dask executing things in parallel. So I'll take a second here to explain. There's kind of two. There are 2 things that Dask is trying to improve. One is adding parallelization where it can, but second is out of memory computation. So if you have a workflow that at some point in its life cycle, perhaps you'd be taking up more memory than your laptop has. If you can chunk that computation you'll into smaller pieces using Dask, you'll be able to execute that computation without running out of memory. So those are the 2, especially in like a laptop setting. Those are 2 things that Dask really makes possible. Okay, so now we'll move on to the first of the kind of dedicated APIs. Of course, delayed has been the flexible parallelize or make lazy any workflow. But Dask.array is very targeted. Dask.array is meant to really recreate the NumPy array as task graph creation, as a task graph creation API. So when you call numpy.random.standard normal, you immediately are creating an array on in memory. But when you call the Dask version of that, you are not creating any data. You're creating a small amount of data, but that data is just the Python dictionary, the task graph that will eventually call a NumPy function to create a set of standard normal functions, all however many chunks you've asked for. So we'll show this with a small example. So we'll import NumPy and Dask.array here. So here I'm calling just the NumPy ones function. So I'm creating an array of length 10, all ones. I can sum this, of course, 1 10 times is 10. But here's a representation of 2 excuse me, 2 chunks. So the first 5 and the second 5, of course, if we add these together, we still get 10. But here is that exact same, this sum of the array of 10 ones broken in half. Here it is in Dask terms. So we're asking, it's the exact same function, but Dask has this extra argument, chunks. And this is saying, give me a Dask array that will eventually yield a NumPy array. But when chunking, go ahead and make each each chunk of my array length 5. So here's the Dask array. As I was saying before, when you call the Dask version, it's not a new array library. It is where you're creating an array with some different representation. You've created a task graph that will eventually be an array. So the Dask version is really just instructions. And so another good thing about using Dask in Jupyter, some of these representations in the notebook are pretty nice. So you can really see what your array looks like. You can see information about the chunks, the structure. It's all very useful information. So of course, the exact same result we'll get by calling some of the Dask version, but we have to call compute to actually get it. Same thing. So the really nice thing about the kind of targeted collection libraries like Array and Data Frame is you can call most of the APIs. There are some things in NumPy and Pandas, some parts of those APIs that cannot be translated into task graph, into a task graph generating form. It just can't be kind of mapped to a lazily evaluated workflow. But most of the Pandas and NumPy APIs are recreated in Dask. And so one thing I'd like to show is chaining something together. So starting with the simplest case is just add. So adding a number to an array, of course, simple operation. But I also wanted to show that one thing that you can do with Dask is instead of calling .compute on a collection, you can pass multiple collections to Dask compute as a function instead of a method, and you'll get 2 results. But one of the things Dask will do is it will inspect both collections and it won't repeat work. So A3 is dependent on A2. And because we're passing in A2.sum and A3, Dask will only compute A2 once and then compute A2 sum and then A3. So it will, the repeated work is avoided in Dask world as much as possible. Something with a few more steps, a little bit more involved. We'll create a bigger array and take a look at it. So this is another just array of ones now in two dimensions with some more chunks, a little bit bigger, and I can do whatever Dask allows. I can do to this array in kind of the NumPy world. So we'll take its transpose and add, do some NumPy slicing, take the mean along one axis. And so this is really building up a number of steps, and we'll see that here when we visualize it. So yeah, here's the task graph for that operation. Not that it has too much meaning, but really just to show that you can really just take the NumPy API, do what you would normally do with NumPy, but say this array was tens of gigabytes. It obviously wouldn't fit in memory in most folks' laptops, and you could still execute it with the exact same API. I'll take a second here to mention Dask optimizations. So I won't go too deep into this. Okay, it's more of a high-level overview, this tutorial. But one other nice thing about the dedicated collections APIs over something like delayed is because they're a little bit more targeted. There are some assumptions that can be made about some steps, and Dask can optimize these task graphs. So when we actually call compute, an optimized version of the graph is going to be computed by default. But when we visualize, we get to see the whole graph by default. So I just wanted to mention here that sometimes one could say, oh, yeah, I have this in delayed. I don't need to worry about trying perhaps using one of the more targeted APIs. There is a benefit. Not only do you get to reuse an existing API, but second, you get to take advantage of some optimizations that exist for array specific and data frame specific workflows that have been built into Dask, because Dask can make assumptions about what's happening in the task graph when it knows that we're operating on arrays. In the delayed case, it's very generic. It's like Dask doesn't make any assumptions about what's going on in a delayed workflow because it's meant to be as flexible as possible. And so it won't be able to add in the optimizations of the graph. Okay, so from here, we'll move on to a quick description of Dask data frame. Dask data frame, I'm going to spend kind of the smallest time on today, mostly because I'd really be repeating myself quite a bit with what we were just discussing with Dask.array, because Dask.dataframe to pandas is Dask.array to NumPy. It's kind of the same idea here, where we take a ubiquitous API. So many folks in the PyData ecosystem have touched pandas before, and so as with NumPy, and Dask.dataframe is meant to just recreate that API in a partitioned way. So it's on each partition of a Dask.dataframe, a pandas.dataframe will be computed, and all of this, all the functions and methods in the pandas world are available to you. Not all, most. So just a very quick example here that we can just take a look at is Dask has a datasets module for doing little tests, and so we can create just this example data frame that has 4 columns, and we can do a group by and grab group by the name, grab 2 of the columns, compute the mean of each of those. And before we compute it, we'll go ahead and visualize it. So you can see so this is quite the workflow. Doing the group by really forces the task graph to grow quite a bit. Same deal, we can just call compute and we get a result. So as I mentioned, I don't want to spend too much time on Dask data frame because really the point here is to show that we have these APIs. I'm really driving this home. We have these APIs that are very popular, used all over the place, and Dask really just gives you the ability to scale them up. Okay, so the next thing I want to talk about is Dask, the distributed project. So far, everything that we've been doing today, and talking about delayed and Dask.array and Dask.dataframe, we've been using the default scheduler, the default execution engine, and that has been just the threads on our laptop. So this will parallelize computation on a laptop. For example, it'll allow you to do out-of-core computation on your laptop. So if you have a 50 gigabyte data frame, you can partition it to do operations on it without running out of memory. But the distributed engine uses this client plus cluster model, where the cluster has both a scheduler and any number of workers that the scheduler is communicating with and telling them what work to do. So the best way to kind of get a first look at the distributed scheduler is to run it on your laptop. So you can create a local cluster with the distributed project. So I will go ahead and create both. I'll bring in the client and the cluster. I'll go ahead and create a cluster. Another useful thing in the Dask ecosystem here in a Jupyter Notebook is the representation of the cluster here. So you can see information when I went ahead and created the default local cluster. So on my laptop, that gave me 5 workers. It's using all of my RAM. But of course, I haven't executed anything at this point. I haven't even connected a client to it. So I'll go ahead and do that. So now at this point, I have the complete graphic up here. I've created a client, or I created a cluster, then I connected a client to it. And so far, all very simply on my laptop. So at this point, I will go ahead and do something that unfortunately folks connected with are following along in Binder won't be able to add this part, but it's okay. The whole notebook will still be executable. So one really cool thing is the Dask the dashboard. So when using distributed, you get access to a lot of diagnostics. And I'm going to pull up two specifically. I'm going to pull up the task stream, and I'm going to pull up a progress bar. I'll go ahead and give myself a little bit more room. Okay. So one of the I think targets for an audience like this is how can I have a cluster that's not just my laptop, and the ecosystem is very fruitful. We have a number of projects that allow users to kind of pull a cluster off the shelf. So there's the Dask Job Queue project, which provides clusters for common HPC systems. There's Dask Cloud Provider, which provides clusters for many of the cloud vendors. Dask Kubernetes. Dask Gateway is a project that allows like a system administrator to provide resources to folks. And there are more beyond this, but I don't want to go too deep into that right now. So I did write a small example here showing the same workflow that I had so far, where I used a local cluster. You could just substitute in HT Condor cluster if you have access to a Condor system. And I created that. I instructed it to use 2 GB of memory per job, then .scale to scale this up to 10 jobs. That would give me 10 workers, and then connect a client to it. And you can pass in a computation to the client, and boom, there you've just sent that task to the cluster. So this is really the power of distributed, the distributed project. So now that I have a local client running, I will compute the same thing that we did earlier with Dask.array. My zooming up here a little bit. The Z, it was this this multi-step calculation I did in the Dask.array with a Dask.array workflow. So now that I have a distributed client and I've got some of my dashboard utilities here, we can compute this again, and it was very fast. but the point I'm making here is distributed has a great set of diagnostics, and we'll do something that takes a little bit longer in a second. But you can go and you can actually see what happened in the task graph execution. And so you can really learn a lot about what may be bottlenecking your workflow or something by plugging into the diagnostics that distributed provides. Okay, so with that introduction to distributed, we'll move on to the final component of today's presentation, and that is adding to the Dask ecosystem here. So especially in the context of a high energy physics workshop. So we have been working, collaborating on for almost a year now on the Dask Awkward project, and we've also worked on the Dask histogram project in the past. And this is to bring native support for both awkward arrays and boost histogram objects to Dask. And so we'll showcase this with a small example. And I do want to note here that Dask Awkward is a ongoing project. It's usable. It's an alpha status right now because it's part of the awkward array, the next version of awkward array that's going to be released later this year, awkward version 2. So you'll notice that when I imported awkward here, I'm importing this v2 submodule. So with that said, we'll go ahead and work out a quick example, and this will be a small, pretty simple one. Like I mentioned, this is a bit of an appetizer for a couple of the follow-up presentations that are coming up. So we'll bring in our imports. So with Dask Awkward, what I'm doing here is I'm reading in a Parquet data set that's on some remote system. So I have a small, Higgs to muons data set stored in Parquet on S3. It's not super big, but I did want to show that this was and the capability to access remote file system here. So if I look at the data set, I mean, this executed very fast. I have a Dask awkward collection from a read parquet function, and it has 50 partitions. So this data set here, there, wildcard had 50 files. So this is partitioned on each file. So, and then in executed terms, if I were to execute this, it would be reading 50 awkward arrays to make one final one. So what we tried to, what we are doing, what we've done a lot of and will continue to do as this project evolves, is exactly what's done with Dask.array to NumPy and Dask.dataframe to pandas. We are doing with Dask awkward to awkward. We are trying to recreate the complete, as much as possible, the awkward API, but just Daskified, made such that all of these, the calls with the Dask awkward version just create and grow task graphs. So the example I'll show here is I'll use the awkward API, but of course the Dask awkward version, to apply some requirements on this data set and grab some value and make a histogram. So using the awkward num function, I want to grab pieces of this data set where there's at least exactly 2 muons. Once I've done that, I want to just calculate the minimum of the muons have a PT, a transverse momentum. So I also want to just grab, again, using the awkward names, using the awkward API, grab the smaller of the 2 transverse momentum values, and then I'm going to histogram that value. So here in the histogramming step, I'm passing in a Dask awkward result as an argument into a Dask histogram function. So there's good interoperability going on here. These libraries know how to speak to each other. So I'll go ahead and execute these cells. Before I compute here, I'm also, I imported hist earlier. I'm going ahead and passing in the result of this computation to the hist library so we can take a look at it. So we'll go ahead and run this, and we'll see on the right, we're going to see Dask, doing its thing. There we go. So you can see I had all 10 of my workers executing in parallel to get this final histogram. So you'll notice I explicitly passed in the optimized graph equals true here. So let's take a look at the difference. And the task stream is going to change quite a bit here. So if I don't optimize the graph, you'll notice there are a lot more things going on. I'll zoom in here a little bit. We had more steps happening. So you'll notice there was a get item call, an equal call, get the num call. So there are a lot of steps that happened to actually execute this result. But when optimized, there was just one step called hist on block. And this, I'm going to kind of bring up again what I mentioned earlier about optimizations. What Dask was able to realize here was that all of these steps that, not all of them, but most of the steps could be executed really as one step. So I will visualize the task graph to show this. So first, this is a little bit of a big graph, but I'll use one partition as an example. We have the reading of the parquet. We're accessing the muons part of the data set. We're doing some operations with the num function, equal, doing the selection, another get item call, then calculating the min, then doing the histogram. And then finally, once we've done the histogram on one of those partitions, we start to aggregate them. So that's why you see this hist aggregate, and eventually we end up with the final histogram here at the very top. So that is the complete task graph. That's everything we've asked for. But Dask will go in and recognize that everything I showed here on the left, this can all be fused together. And one of the huge gains from that is every single time Dask computes a result and is going to reuse it, it may need to be communicated between workers. And when we can reduce the amount of communication between workers, that's overhead. And so Dask will optimize this graph and fuse many of those parts that all get sucked into one step, really. And so everything that was in that kind of long column basically was able to be combined into a single step here. And it just takes the name of that step, histone block. But the power of using a dedicated API, targeting a dedicated collection, targeting a specific API, is Dask is able to bring in these kind of optimizations. So this is just one more time I wanted to mention the delayed is very powerful in that you can turn any Python workflow into something that can be executed as a task graph with Dask. But there's really a lot to be gained from starting a project like Dask Awkward and Dask Histogram, where we can recreate these APIs and do things a little bit better than perhaps delayed would be able to do. So I've spoken to folks who've had the question, oh, like, why not just, delayed exists, why not stop there and just implement everything with delayed? It seems powerful enough. But there's really a lot to be gained from these dedicated libraries. Okay, so those are the examples that I wanted to show today. So then I just wanted to wrap up with a few minutes on some final thoughts here. So as I already mentioned before, the Dask universe is large now. The project has been around for quite some time. And so we've really just scratched the surface of what one can do with Dask. But hopefully this was, hopefully you gained something from this if you hadn't seen any Dask before. And if you have, hopefully you saw a little bit more. There are a lot of resources available. The official Dask documentation is quite large. And there's also a longer tutorial. Of course, this is about 45 minutes. But there is the official Dask tutorial is meant for 3 to 4 hour setting. The kind of final call to action here that I wanted to mention is that the Dask Awkward project specifically definitely welcomes folks that are willing to live on the edge a bit. And please stay tuned for some follow-up presentations that, like I mentioned, will showcase more connections between the Dask world and Scikit-HEP. Yeah, going back one more time to this call to action for people to use Dask Awkward. Like I mentioned, it's in development. We're working in parallel with the work on Awkward version 2. So if perhaps you're using Awkward and you're getting ready to transition to being able to use Awkward version 2, for example, and you see yourself as perhaps having some value in adding Dask to your stack, please give this a shot. We have a lot of the API implemented, but in kind of the Dask world, a lot of things come into the libraries on a user feedback basis. So folks will come across a function or a method in NumPy or Pandas that they need for their Dask workflow, and perhaps it hasn't been added yet. And it's very common for people to come to the Dask community and say, hey, I'd like this. I'd like, obviously numpy.transpose is implemented, but say numpy.transpose wasn't implemented. You come across that, you can just go to the community and say, hey, can we get numpy transpose added as Dask transpose? And usually there's someone, if it's possible, there's someone around that's willing to add that. And that same pattern we expect to adopt in Dask Awkward. If there's corners of the API that don't work in the Dask workflow, we'd be happy to work with anybody that needs that. So that's everything I had for today. Looks like we have a good bit of time for some questions. And yeah, thanks for your attention.
Thank you so much, Doug. That was very clear, and I think you explained everything nicely, but also got to some really sort of quite interesting examples in that last section there. So we do certainly have time for questions, and just a reminder to people that you can ask more of them if you go along to Slido. Let's start with the first one that was asked by Michael, which you asked, can Dask optimize or automatically determine the chunk size? Could I ask Dask to ensure that chunks are no more than half my available memory?
Yes, there are some Dask configuration options. So there's a blog post even that goes into I can actually go to, while I'm sharing my screen, blog.dask.org. Yeah, choosing good chunk sizes in Dask. This is blog.dask.org. There's a paradigm around chunking. So I'll mention, yes, Dask will try to automatically do things, but it is worth spending a little bit of time thinking about this. There's, like I mentioned, there's configuration options, and then Dask will, depending on the size of your data, how you've partitioned it, there are some automatic things, but in general, it's good to think about this and test, actually, like create some small test cases and see if your chunk sizes are a problem, for example. Yeah, I hope that answers the question.
Oh yeah, that's a really good resource for answering that question. Clearly, you can dig into a lot of detail there. Let's just also deal with Michael's second question, because I think it was answered in the presentation. He asked if Dask delayed was implicitly parallel. I didn't notice any declaration of thread resources.
Right, yeah, so I would say the execution engine is explicitly parallel. So whatever task graph gets created by a delayed workflow. So I'll go back to this example that I showed. So this graph was created with delayed. The delayed itself doesn't necessarily know to create something that is parallel, but the task graph, its structure, and this structure is obviously parallel. This calculation, for example, I'll drag it over here, is completely independent of this read tree. So obviously this calculation is dependent on this read tree. So the execution engine will go in and see that I can execute read tree calculation over here on the left-hand side at the same time that I can execute read tree over here. So it's not necessarily that delayed knows anything about parallelization. It's once you've completely constructed your task graph from delayed operations that the execution engine will go, oh, hey, look, this doesn't have any dependencies. I can execute it at the same time with this other thing that has, different dependencies or something like that.
Okay, that's great. Thanks very much. Let's switch it up. Let's go to Doug's question. I guess you're going to ask a question live, Doug.
Yep.
You go ahead.
Yeah. As I'm a resource provider, so one of the things that using a Condor queue, there's obviously scheduling time to spin things up. Are there settings so that multiple workers can flow into the remote object, the remote, job slot?
There is an
and just keep using it, and then eventually, shut down at a time limit.
Yes, there are features in the cluster in the cluster library to adapt. Yeah, there's a scaling and adapting kind of a max and min capabilities. Yeah, those I don't have any personal experience with at this point, but I know that there's functionality there.
Right. Thanks, Doug, both of you. Okay. Nice question. Let's go to the next question. So Eduardo was asking a bit more about the future of the Dask and PyHEP collaboration. So if you're going to get any insight into what's on the horizon and how people could engage even more in that, because that's obviously something that's very interesting for our community.
Right. Yeah. I'd say, like I mentioned before, stay tuned. There's a couple more talks coming up, but I will just kind of give a little bit of a spoiler. One of obviously the talk description is there, the abstract for the next two, so you can, not really a spoiler, but we're gonna hear a little bit about connections between Dask and Uproot. So reading root files directly into Dask collections. And I purposely skipped over that a little bit by using a Parquet data set. And secondly, we'll hear about some being able to access remote file systems. And that's a big thing in Dask. I mean, a lot of, I'd say the majority of people that use Dask heavily are using some, for example, the Pangeo community has large data sets, obviously not stored on local systems, stored somewhere in the cloud, and so it's a big thing in the Dask world to be able to access the Google Cloud, AWS, whatever, some remote stuff. So connecting xrootd with the kind of platform that exists in the Dask universe called FSSpec, connecting those together is something else we'll hear about. And obviously, I mean, Dask Awkward is relatively young in the scale of the, Dask has been around for since about 2015, if I remember correctly. And, we started working on Dask Awkward last year. So we'll be working on Dask Awkward for a little while longer. We also have another project that we're collaborating with Awkward folks on for better Pandas support and Awkward. So the train is moving, and there's more to do.
That's great. Sounds like quite an exciting time to be involved in that and keeping an eye on it. Okay, grand. Let's go to the next question, which is, how do the cluster workers communicate with the main node, and do you need a shared file system to make this work?
So you don't need a shared file system. There are a few communication protocols. Unfortunately, I don't know the nitty-gritty details, but serialization matters a lot here. So in Python world, the objects are serialized and then sent over the wire, so that, but Dask does try to do this as well as it possibly. This is one of the I'm not super involved in the distributed project. But having spoken with some of those folks, it's always a pain point that they are very aware of, always thinking about. And Dask does try to limit the amount of communication that has to happen over the wire, and limit passing big objects, for example. But that really how the clusters communicate, the components of the clusters communicate by serializing objects, be that data or functions, and passing it over the wire.
Okay, great. Thanks.
Shared memory, though, is something that's being explored. It's been explored in the past, but it's being explored again by one of my colleagues. And there's actually likely, I'm going to plug, there will likely be a presentation later this year at PyData Global on trying to use shared memory in Dask.
Okay, that sounds very cool indeed. All right. Then let's go to the next question, which is just, I think, a reprisal of what you were saying. To summarize, is it fair to say that the reason to use Dask data frames, array, etc., is just that compared with delayed, they have further optimizations?
That is certainly a main component of the argument, I would say. But then secondly, you'd be recreating the wheel in a lot of cases. A lot of work has gone into being able to kind of drop in replacement, the import. So I wanted to highlight the optimization because I think it's a cool thing to see. It's nice to see that real benefit. But even beyond like runtime efficiency, the recreating data frame group by with delayed, I can't even think right now, right? Like it'd be a project. So there's obviously a huge benefit as well to having that existing API in terms of just being able to produce code quickly, get things moving.
Right. Well, indeed, of course, that's one of the reasons that we like Python so much, is it makes people efficient as well.
Yeah.
So yeah, we care about that a lot. Okay, that's very good. And then there was another question just about the list S expression, but I think that was pretty much answered by Jim, actually, that it was just a way of representing the graph in this particular case, unless you have any more insight into that.
No more insight. I like to point out that it's like an S expression because before I ever used Dask, I had played with Lisp. And so when I saw that comparison, it really clicked for me. So for anybody else that perhaps had that experience, I wanted to just point out the connection between S expressions and a delayed function call in Python.
Very nice. Thanks very much. Okay, so we've gone through all of the questions on Slido. So last call, if anybody wants to stick up their hand and ask something. Going once, going twice, going 3 times. Okay, it's a no, right. So thank you again, Doug. That was really nice, and thanks for taking the time to answer all of the questions as well. Great presentation. So let's move on now. So we'll go to where we stay very much in the Dask universe, actually. And we go to a lightning talk from Kush, who will tell us about Uproot and Dask. So clearly following on nicely from what Doug was just telling us about. So Kush, I saw you before. Yes, I can see your screen there. So fantastic. I just let you take it away. Yep.
Hello.
Hi, can hear you very well.
So thank you. So hi, I'm Kush. I worked as a GSOC student under Dr. Pivaski this year, and where I worked on integrating Uproot with Dask. And my work introduced a new function, uproot.dask, that makes it quite easy to integrate the root file reading facilities of Uproot with Dask. So I'll just get started right into the lightning talk. We just import some things and we set up like the paths of all the small root files. For this particular demonstration, we'll mostly be working with very small root files. And in the end, we will have a small demo with a larger root file too. Eager workflows. So just before we start with Dask workflows, we'll just look at how eager workflows already work on root. So first, if you have the file name, you just open it, and then calling .arrays, like Doug said, this is where the T-branch data is actually read into memory. By default, .arrays returns an awkward array. And through the computations, like the entire T-branch data is read into memory into the awkward array, and through the computations, all the awkward arrays are materialized eagerly. So if you just have a look, you'll see the calculation is already done. However, this is not really the best solution, especially when you have larger data sets, mostly because a lot of them don't fit into memory. And like Doug basically said, Dask is useful when you're trying to work with data that doesn't really fit in memory, because it provides you the capability to chunk entire larger data sets into smaller chunks so that you can work on them one chunk at a time. So while we're deprecating uproot.lazy in favor of Dask, because as Doug demonstrated, there are many advantages. So essentially, uproot.dask provides an easy to use Dask workflows to delay and parallelize the file reading functionality already present in Uproot. I'll just run stuff. So normally the way you would expect to do it, after mostly like Doug put in his first example, you would expect to use Dask delayed. You'll the array function that I mentioned over here that actually reads the t-branch data, you would expect to wrap it in dask.delayed and then call it as a delayed object. And then when you need it, when the computation needs to be done, you will run compute on that. This is what you would want, you would normally do. But approved.dask provides convenience, a layer of convenience over that, in the sense that when you do run approved.dask on the file name or the file path, you can just, it directly gives you a Python dictionary of Dask arrays or a Dask awkward collection. I'll come to that, but this is just I'm trying to show the shift in paradigm as well as the convenience that approved.dask provides. So coming to what approved.dask actually returns. All the approved functions, like all the other approved functions, they follow the convention that we have a library argument that can either be set to library equal to NP or library equal to AK. With library equal to NP, approved.dask returns a Python dictionary of Dask arrays. So yeah, this is a Python dictionary. The branch name maps to the Dask array, and the Dask array, yeah, maps to the Dask array. You might want to note that the data is not been read from the file yet. This is just the array, and only when you call compute will the data will actually be read. Dark also introduced the Dask awkward data collection. So approved.dask uses that as the default return value. That is, when library is equal to AK, the default value, it returns a Dask awkward collection. So it's a brand new Dask collection, and it supports a good majority of the computations actually being done supported by awkward. So this has, as normal as you would expect, when you call compute, you can it deals with jagged arrays and everything. Another feature of this is when you have two files. Just for example, I'm using another copy of the same file with a different compression. But when you have two files with the same branches, the common branches are concatenated together. For example, if we just see, if I run this, the shape of the first one is just approx 2300, and the shape becomes twice. So all the common branches get concatenated. In this case, all the branches are exactly the same, so all the branches will get concatenated. Then something Doug did talk about was also asked on Slido was about chunking, right? How do we control chunking with approved.dask? So essentially, we have a step size parameter. You might recognize this is similar to the approved.lazy API. There is also a step size parameter over here that can give you an approx size of the chunk that you want. So this accepts either strings or numbers. So when you don't call it, when you don't actually have it, it's an implicit value of 10 MB. So in this case, it's taking the entire chunk size as the entire array. It's a single chunk. But when I tell it that every 10 records should be a single chunk, that gives me the ability to set it. The same thing extends to Dask awkward also. Yeah, it allows me to set the number of partitions that I want over the entire Dask awkward array. Yeah, after that, we also have opening files. So from what I understood by talking to people is that sometimes each single root file might fit into memory, but the entire file, the entire data that you want to actually calculate or make calculations on is split over a lot of root files, like hundreds and thousands, which might actually not, fit entirely into memory. So sometimes opening the root file also needs to be skipped until the compute call. Right now, approved.dask does open the root file, but does not read any t-branch data. It does not read any t-branch data. It just reads metadata like the number of entries in each t-branch, etc. So with approved, with open files is equal to false, approved will not open will not open the files except the first one. For example, if you have a large list, just look at this. When you do provide a list with open files is equal to false, and you have a rather large list of values, that is where you can use, like, the advantage of open files actually comes in, that it opens just the first file, looks at the T branch metadata, and from that it assumes the keys and the sizes, not the sizes, but the chunks as the rest of the files. So when you do call this, whether you open the file or not, in the end, the arrays, the materialized array in memory will always be the same. So I'll just compare an eager workflow that we saw before over here to a DAS delayed workflow. This is a simple conversion from Cartesian coordinates to spherical coordinates. So if you do this, you just give it the path to the T tree, library is equal to NP, and you set a step size. Step size, if you don't set it, it's also okay. This is not a very big file, but I'm just setting it specifically to show how the DAS chunks are visualized in this case. So you'll be able to see that essentially we have 3 chunks in this case, because this is like 2300 records, and each chunk has like 1000 records, and the last one has 300. So all these can take place in parallel, or at least in a multi-threaded scheduler. When I do call compute on my single machine, that is, it uses the Dask inbuilt multi-threaded scheduler. So these are just some of the graphs that you can get. And again, you should note that no data is being read in actually visualizing this. Data is only read when you do call the final compute file. Yeah, that is at this point. Right? So yeah, that brings me to the second part of the thing, where I demonstrate the same approved.dask with some real world data. I'm told this is a very famous data set, and yes, it's another ZP. So just import some things. Yeah, one thing is important. Doug did introduce Dask distributed in the end, and he talked about clusters and that. So these same Dask workflows that you create using approved.dask can be run in those same clusters. One additional advantage that this provides is that it provides certain diagnostics, and I'll be using that. So I'll making a very small lightweight cluster, and we'll look at some of the diagnostics we have. Yeah, so this is a very lightweight cluster, not a lot of memory being used. So this is the simple code for a very simple ZP. And yeah, you can see we are using Dask awkward functions over here too. So at no point over here is any computation or any data reading actually being done. Will we visualize some graphs too? As we actually do the computation, I'll come back to these visualizations and how the optimizations are done in this case. But looking at the computations, once we start, you will notice that the memory actually starts to increase. So Dask has started to read the data right now. And once we are done with a few tasks, they'll start appearing on the task stream. This is some excellent tool by Dask Distributed. It gives you a good info about the kind of tasks that are processing. As they come into memory, you will get more tags. They'll turn red. Yeah. And once they're done, they'll turn blue. So even if you are running on clusters, this is a good tool to, kind of understand and figure out what's going on with your entire machine while it runs. Coming back to the task graphs. Just a sec. So this is a rather very huge file, so it's taking some time. So yeah, so I mean, I kind of think it's very interesting. You get to see all the actual formulae that you code actually take, you know, actually see the task graph that is behind this. But the lucky thing about this is thanks to the help of Doug and Martin, we are able to optimize it in ways, like he said, that all the chunks that could be merged together, or all the tasks that could be done at the same time, were merged together in single task. And this is the final optimized graph that is being run on the cluster. So this is done. This was done in 91 seconds, and this the plot regarding that. So any questions regarding this, or do we have time for questions?
That's great, Kush. Yeah, we're a little bit short of time at the moment. There's no questions in Slido. If someone wants to throw their hand up very quickly, we could probably squeeze one in. But if not, then I guess everything was very clear. So thank you very much again, Kush, for that presentation. So let's move on then. Staying with our Dask theme to the talk on enabling Dask interoperability with XRootD storage systems. So this is a lightning talk from Scott, who's going to tell us about that subject. Obviously, it relates very strongly to what we were discussing with Doug's talk earlier on. Kush was showing us. So Scott, are you there? Oh, I won't see Scott. Aha. Okay, well, if that's the case, then I guess we might want to carry on. Francois, are you with us?
Hello.
Hi, Francois. Do you mind if we just bump your talk up by 10 minutes?
No,
and we'll
fine.
see if we can come back to Scott later on.
Okay, it's fine.
Yeah, so, okay, we're going to leave Dask now. And actually, this is a talk I'm really looking forward to because this is very interesting. A quick talk on why Python is a good choice for making digital twins for industry and research. So I will let you get going, Francois. Share your screen, and you can tell us about this subject.
Okay, I will share my entire screen. It will be easier, I think.
That's whatever works best for you.
Yeah, give me one moment. Yes, I think. Okay. Do you need to see my face as well, or is it irrelevant?
Entirely up to you. No worries either way. So we can see your whole screen. It's not in full screen presentation mode.
Yeah, it's not yet in full screen. Yes, that's correct. Sorry. Okay. Okay. My camera is disabled by the host. Anyway, let's start. It's okay. It's fine.
Okay.
So I have maybe something like 8 minutes, and then 2 minutes of question if people have questions.
That would be fantastic. Yes, I'll let you take it away. Thanks a lot.
Okay, so I'm François Gutters. I'm a technical director at Arfon 3D, and what we are doing at Arfon is striving to bring open source real-time 3D and virtual reality technology to the Python ecosystem. I think the most relevant use case of VR built in Python we worked on is the behavioral study conducted on behalf of the French National Railway Company. We built it jointly with ErgoCenter, which is a team of PhD experts in behavior and ergonomics. The problem we have in France with small train stations is that pedestrians are requested to cross the railway using what we call PTC, pedestrian track crossings, and approximately 15 lethal accidents occur each year. So the French railway company is constantly trying to improve the way to avoid these accidents, either by using visual pictograms or audio signals, or of course, pedestrian chicane barriers. You can see a photo here of what it looks like to cross the railway. The best way to conduct a safe and reliable experiment was to remove any external bias. And so for this reason, we decided to build the whole experience in virtual reality, allowing the behavior PhD to conduct the very same experience in the very same conditions on the hundreds of users. We help them to build an experimental framework using Python. So everything was done in Python. Everything you will see. We started to model the whole train station. We model it in 3D in full scale, including pedestrian, chicken barrier, of course, which is the most topic of the study, and the train, obviously, simulating arrivals and departures. So the trains, when you are in VR, are in motion. This is a facility where the experiments occur. It's 80 square meters, allowing the users to experience what it feels like to walk across the railway station. So in this context, what is virtual reality all about? Virtual reality, sorry, is either sending data to the brain or extracting data from the brain. In our case, we extracted as much data as possible from the user's brain, using all the Python tools and hardware we had at hand. The Python ecosystem, in our case, allows us to connect both hardware and software tools that usually don't work together in a very simple way. As you can see, we have the VR headset, we have cameras, we have, of course, a PC. So our Python experiment is running on the desktop PC and not in a Jupyter notebook. I'm sorry about that. I have a short video. So the VR simulation, maybe I can put it in full screen, not that better. The VR simulation is running on a powerful, as I said, desktop PC, just one desktop PC that sends the VR image to a wireless VR headset, allowing the users to walk freely. The headset will send back the position and velocity of the user head, his heart rate, and the direction of his eyes, which is very important, as you will see. To build a complete experience, we use external speakers to reproduce the ambient background sound of a station, including audio alerts, train arrivals, departures. And each user session is also recorded in video, as you can see here. The extracted data will tell us the position of the user, its walking speed when entering the PTC, which is very important for us, and how much is paying attention to the audio signals, the pictograms, and if he's scanning visually his environment, if he's watching the ground instead, which is not a good thing when you're crossing the PTC. Why is Python? The benefit of using Python is, for us, is that it allows ultra short iteration cycles. The whole project was created in a course of 3 months with 2 developers and 2 3D designers, plus the PhD who designed the whole experiment. So it's a very, very tight schedule. And for us, Python was a real advantage over C++, for example. Python brings a complete ecosystem for data storage and analysis, starting with SQLite and NumPy, you know the drill. During the analysis stage, Python orchestrates the whole session. It triggers the video recording, it runs the VR simulation, it grabs all the data, storing them with a timestamp in order to make sense, in order for the data to make sense when it comes to draw a conclusion. Python is open source, and so we are. Fond is open source. That's very important to us to avoid vendor lock-in, and we want to be able to share the code from top to bottom. Now for the results. What you can see here in this beautiful screenshot, which doesn't make any sense at this point, is a point cloud generated from the data acquired during the experiment. So it's a compilation of all the data of the 100 users that experimented the VR simulation, and everything was stored in a SQL database. So what do we get from this? This is the PTC, the pedestrian track crossing. Several scenarios we're testing with or without the chicken barriers. And what we can see is that the impact of the chicken barrier is not what we expected. On this point cloud, you can see that the eye contact of the users on the environment, we can see that the security pictograms receive less attention when the barriers are enabled. On the contrary, without the barrier, we found the attention of users was far more focused on the pictogram. I can go back and you can compare both. This type of valuable information has been, we've been able to extract, this is the information we've been able to extract from this VR experience. But Python and VR is not only useful to conduct human factor studies. It helps a lot in machine learning, especially when providing a visualization toolbox that works in real-time 3D. So real-time 3D is, of course, interactive 3D, three-dimension images. During the past years, we built an open source sandbox to simulate aircraft and flight environment. Again, it is entirely built in Python. The main benefits is the ability to connect the simulation to the machine learning ecosystem in Python. It's huge. The sandbox is able to run thousands of simulations when one or several planes, are controlled by a neural network. The 3D rendering side of the sandbox helps to visualizing the result. We can deal with realistic materials, atmospheric simulation, terrain modeling. I have a video here. Maybe I will skip it a bit because we are running out of time. So this is me using the VR simulation. So it's not a flight simulator. It's just a Python program that's run in real time, send image, VR image to the headset. And as you can see, it runs on a very classic laptop. This platform was used with success by several universities, and you will have the links of the scientific publication in the last page of the presentation. So I will skip to the next topic. Besides human factor and aircraft simulation, for us, Python provides an almost natural environment to simulate robotics. This is a rich, it's a really affordable robot designed by a French startup, Pollen Robotics, and we decided to build a digital twin that would be open source from top to bottom. To build a digital twin, we just need to be able to read the URDF file, which is a descriptor of what the robot looks like. And we need a robotic-oriented physics engine. For that, we use PyBullet, which is very handy and comes battery included in Python. So I can show you the result again. So what you see in this video is a live capture of the VR simulation. The human operator is actually, I can show you, is actually manipulating its wireless VR controller, the same you can see in the video. I have the same in my hands, actually. And the inverse kinematic is computed entirely by PyBullet. Does everything else. And what we just do with our phone is rendering in VR. So the human operator, as it said, at the place of the robot's head. It's a very cheap and straightforward prototype teleoperation. And just this demonstration fits in less than 500 lines of Python code. I have just one last demo. I will just show you, and if you have any question, I'm open to any question. As maybe we're just 5 seconds left. Are there any questions?
That's great, Francois. Well, there's no questions in Slido yet. Oh, no, wait a minute. There's one.
Yes, there is one.
Yeah, I see. Yeah, Eduardo's just asking if you have any specific suggestions as to where this could be interesting in high energy physics.
I think there is one interest in 3 dimensions. It's that you can display something else than a reality modelization. Maybe if you have tons of data in several dimensions, even if it's not 3 dimensions, maybe you can have 4, 5, 6 dimensions. It makes sense to display them in 3 dimensions and even to experience them in virtual reality. So I think you are able to take any kind of data sets and display it in VR and probably switch very quickly from one selection to another selection of data on the one column or one row for another row very quickly in VR, and maybe you will be able to make sense to the kind of computation you can run on your own data sets.
Yeah, that's really interesting. I think the thing that comes across to me from your presentation is I had not realized how what the great integration was between Python and things like 3D rendering software.
Yes.
I didn't know about anything about that, but it's clear that that actually works really well.
Yeah, that's what we do. We worked on making Python really efficient in 3D and virtual reality.
Right. Yeah, that's great. I'm sure that people in outreach in particular could think of lots of good things to do with that as well, sort of virtual detector visits and things like that. Eduardo, did you want to ask a follow-up question?
Yeah, hey, thanks. Yeah, quick follow-up. Well, so just to ask you, given that we poor people in HEP, if we were to collaborate on things like a little project or to try out something, is that I mean, how financially speaking, to be blunt, is that go? Do you have any way of collaborating without any specific funds?
Sorry, I didn't, the audio quality, I didn't hear the question.
Yeah, just to ask, if you were, imagine we have now an idea we would like to try out with you. Do we need any specific funds, given that it's so difficult in general in hydrophysics to get funds for small little projects here and there? How would that work for you? By funds, you mean money? Yeah. Okay. Yeah, I just wanted to be sure. I don't think, well, on a strict licensing point of view, everything is open source, especially for research field. So you just grab the engine, it's for free, and that's pretty much it. You will need experts, I think, in 3 dimensions, people who are able to bring models, 3D models, to the engine. That's all. And obviously, experts needs to be paid, but that's pretty much it. Okay, I see. Thank you.
Super. Thanks, Francois. It's very interesting to hear about this talk from sort of like something that's quite different from the work that we normally do. Yeah. Okay, I think that Scott has been able to make it along. So I think what we'll do is just jump back one talk in the agenda. So we go back to our Dask mini session. You there, Scott?
Yes, I'm here, and I apologize for missing my meeting time. I had it mixed up with the time zone.
Not to worry, we're still in the same session. It's all good for us. So let's get going on that because we're running a little bit behind schedule. And you have 10 minutes for the lightning talk on the interoperability with XRootD storage systems. So I'll let you take it away.
Okay. I'm going to share my screen. Here we go. Okay, so I guess we'll start now. Now, it won't be too long. It'll be, but yeah, okay. So so I worked on a IRIS fellowship internship this summer, and I worked with Nick Smith and Jim Bawarski to develop what's called an XRootD implementation for FSpec. And for those of you that don't know, within the scikit HEP like ecosystem, there's a file system standard called FSpec that other tools within the ecosystem use to talk to different servers and data storage systems. And one of the biggest ones is Dask, right? Dask is it's a large data set analysis package that's used very commonly. And up until now, Dask and other tools that use FSpec would not be able to talk to XRootD enabled storage systems, right? And my project was to make it so that FSpec is compatible with XRootD storage systems. And I do have a little bit of a demo file to show how that works. Yeah, so I guess this demo file, it's not available currently on the repo, but I think I am going to make a publicly available version. So okay, so we'll take from the top. In order to use this implementation, you have to have like Dask installed, FSpec installed. And all you have to do is pip install fspec extrude in your environment. And that's all you got to do. It's up on PyPI. So starting from the top, it's just a simple text file example, right? Where on my machine, I have a local extrude server running, and I have a text file. I'm going to write a text file to the server, right? And you run this code and it works just fine. All you have to do is fspec.open and input the path to the server. And any path that starts with root refers to an extrude server. So before, you wouldn't be able to do this with fspec. If you just have a root file path here, it wouldn't do anything. But now it does work, and I guess this block of code does not output anything. But the next code where we read from that file that we just wrote does work. So let's run it. There we go. Right. So it's able to. So the implementation gives pretty much all of the standard features that fspec requires, all the same standard features. So it lets you read the whole file with f.read. You can seek to any location, read a line, or read a specific number of characters from your starting position. And here, so we wrote some test data, and then we're reading that test data in the printout here. It also lets you do appending, and that's pretty straightforward. And it does all the basic file system stuff.
Scott, could I just interrupt you just for a little tick? Your screen is actually the fonts are very small. I don't know.
Small?
If you zoom a little bit on it. Yeah.
Oh, I apologize.
Over video, it's kind of hard to see.
Yeah, let me, I never actually thought about adjusting that. I don't know.
Browser by holding down Control and then, Command.
Yeah.
There we go. Oh, all right.
Yeah, even one that's much better. Yeah.
Okay.
That's clear now. Thank you.
I apologize for that. I just never really noticed it before, but it is pretty small. But we're good. Okay. Thank you for pointing that out. Okay. Yep. So I've showed it works with all your basic file reading and writing stuff, but it also has some server or file system operations. We're able to search directories, get info about a certain file. And I just have some demonstrations of that. Like here, I'm going to populate my extrude server with some sample files. Let's do that real quick. There we go. And yeah, here. So here we're going to list some. We're gonna list the files at the demo directory, and you can choose to have more or less information about them. I know this looks like a mess, but the first output is just a list of everything at that directory, and the second is a detailed list where it gives you everything, like all the stats about the file. And one of the most useful features is cat ranges, where you can read multiple data sets from multiple files, and that's what we have going on here. It took a little longer to make that work than I expected to, but it's all good. And of course, it has both fspec extrude has both asynchronous and synchronous functionality, right? So when you create your file system object using the standard fspec function here, you just specify that you want it to be asynchronous. It's synchronous by default, but you set asynchronous true, and you can run things asynchronously, right? And it handles all that just fine. Here's a simple example running two things concurrently. And that's the last thing, and this is the most important part, is that now Dask is able to read from extrude servers, right? So you have your standard read CSV in Dask data frame. And now you can just give it the URL of your XRD server. And I have a CSV file in my server currently, and it'll read that CSV file. So I mean, that's it for the demo, but it's pretty straightforward. Right now, if you want to access data on an XRD storage system, all you have to do is give Dask or FSpec your the server URL, and that's it. I mean, some future, well, I guess this project is, so the core of this project is done. I did finish that this summer, but some future improvements we want to make is to make it so that not only can Dask read from XRD servers with the simple URL, but also read root files, .root files with just a simple URL as well. And to make that happen, it involves a Dask uproot, implementation. And something that my mentor had been working on is an uproot FSpec source, right, to make that all work together. That is not complete yet, but that is future work that might be coming soon. But for now, this FSpec XRD implementation is out, it's working, it's ready to go on PyPI.
Thank you
so much. I think that's it.
Yeah, that's really nice to see that development, given the relatively ubiquitous nature of XRD interfaces on this kind of storage systems that we run in HEP. So there aren't any questions, which I think means that everything was super clear. And I think in the interest of time, we should probably move on because we're running a little bit late. But thanks again, Scott. And we'll move to the last talk of this session, which is from Baijananth. Sorry, I probably made a complete mess of your name. But you're going to tell us about using C++ from Numba, fast and automatic. So we transition back a little bit to the C++ world now.
Okay, can you hear me?
Yeah, we can very well, and we can see you too, and we can see the screen. So I will let you take it away. And yeah, we have, in principle, half an hour. If you're a little bit faster, that would also let people get more of a break. But yeah, on you go.
Yeah, okay, no issues. So hello everyone, I am Badinath, and I am an intern at CERN. And I have been working on one of the projects that I've been working on with Vasil and Wim is how to use C++ from Numba. So most of you must know about PyRoot, and PyRoot has enabled the use of root-based data models in various experiments in Python. And while this has led to people use Python libraries and functionalities, most of these native features of Python, such as loops, are very slow. So people tend to stray away from them. Now, Numba is a package that allows numerically heavy programs to be written in Python without skimming on execution speeds. It translates Python function in basically native code using LLVM compiler framework. And up till now, PyRoot objects were not supported by Numba. This led us to combine both of them and create an extension for PyRoot that enables the use of PyRoot objects inside Numba-jitted functions. So it allows Numba to determine the types of PyRoot objects and efficiently JIT them, converting them into machine code. Let's first go over how Numba really gives us the performance that it gives us. So Python has the flexibility of converting easily between different data types. And this is because each data type that is stored in Python can be represented as a Py object. So let's say you have a statement f is equal to 0.5. So this 0.5 is first converted into a Py object. And this Py object's pointer is what is stored in f. So this process of converting any native value into a Py object is called boxing. And now let's say you want to square the floating point value. You have to convert the Py object back to the native value to do that. And Python calls it unboxing. And once you have unboxed it, you can calculate the square of it and then box it again and store it back into the variable. So these operations are obviously detrimental to the performance, but they are also necessary for the flexibility that Python provides. Now, number doesn't do all of this. It simply unboxes the input to a function. It passes the input through the native code that it has generated, and then converts only the output to the Py object. This gets rid of all of the unboxing operations that would have otherwise taken in the function, and it speeds up the operations by a lot. So for this to work, first of all, number has to know the type of the input, the output, and the type of the intermediate variables. And once it knows all of this, it can convert the function into native code. But what if number doesn't get to know about the types? Then it will spend the same amount of time unboxing as Python would, and the speed up will be minimal. Let's measure the performance that we get from number. So for that, we use a math-heavy function shown below. Here we calculate the tanh of the trace of a matrix and add it back to the matrix. Now, if you see, we have two functions, one that runs in pure Python and one that is jitted with number. Now, the only difference is the JIT of decorator that we have. And in this, we use no Python is equal to true so that we can instruct number to not have any unboxing or boxing operations in it. So if number is not able to find any type that it doesn't recognize, it will fail the compilation and not proceed forward. And this decorator is the one that instructs number to compile this into machine code. So measuring the execution for this, so we measure it in this way. First, we measure the warm-up time required by number. So this warm-up time is what number requires for loading modules, compiling the function into machine code, and then running the function. But if once the warm-up is done, number is much faster than what the Python function will give us. So this is where number is really used. So if you have a function that runs on the same data type for a lot of times, number will be able to convert it into machine code, and you will be benefiting from a much faster speed than what Python can run. Now let me introduce you to CPPYY. So CPPYY is an automatic runtime Python C++ bindings generator, and it is used to call C++ from Python and Python from C++. So it's the core of PyRoot, which is why the number extension that we designed was originally with CPPYY and then later ported to PyRoot. And since the extension can be used with CPPYY as well as PyRoot, we will discuss how to do both of them. And you will see it's very similar to use it in both, and you can basically interchange CPPYY for PyRoot when using this extension. So you would say, what do I gain from using this extension? So first of all, number makes loops fast. So before when you were using CPPYY or PyRoot with Python, the loops with the Python would be very slow as compared to C++. And number alleviates this problem, and it can make the loops as fast as C without much code instrumentation. You code completely in Python, so this makes debugging easier. To debug any number instrumented code, you just remove the instrumentation line, comment it out, and you are basically now debugging Python code. And if you want to debug number code itself, you can use the GTB function in number. And it also has a variety of flags that can be used to see tracebacks and intermediate steps that are taken by number, and you can find the bug that you are looking for. So this is obviously easier to debug than a code that is set up in Python and uses RDF for hotspots. RDF is root data frame, of course. And we do not have any conversions in the machine code. It converts cleanly. So there is no boxing or unboxing that is required, and we gain the maximum speed up that is possible. So the extension also allows both of the worlds of Python and C++ to be closer together. You can easily switch between C++ and Python as and when you want. Moving on to performance comparisons, we use the same function that we used before, and we just replace np.tanh with cppyy.gbl.tanh. So this says that the tanh is in the global scope of the C++, and we want to use that instead of the np.tanh to basically compare the performance. We import the extension first, and then we run this function. Again, we measure the warm-up times. And if you see, it's almost close to the number function, the warm-up time. It's slightly lesser because number has downloaded all its modules, but it takes the same amount of time to compile the function into machine code. And even the runtime is almost similar, which shows that CPPYY has very less overhead on number. Moving on to the features that the extension provides. So first of all, it's extremely plug and play. So you just import the extension, and then you can use any C++ functions inside number jittered functions. Let's say here we are using the sqrt from the global scope of the C++. And we can use it to calculate the square root of 4 and pi, and you can send data from Python into C++, obviously. Coming back, we have the second feature that we have is template instantiation. So CPPYY already had a support for template instantiation, and if someone has coded in C++, it's a very important feature to have, because it's used abundantly in code bases, and you cannot use a lot of code bases without supporting template instantiation. So this extensions also works with templates, and as you can see, we have the square function that is templated, and we pass a matrix that is of float type as well as of int type, and it can calculate the square of both of them. Similar to the template instantiation thing, we have overload selection. So let's say you have a function that is overloaded for different data types. Like here we have mul, which returns x into 2 if you are passing in an int, and x into 3 if you're passing in a float. And we again pass the array of floats and ints to see that it is correctly selecting the overload based on the input that is provided to it. Next up, we have the demos. First, we have an example that is directly taken from the number examples directory. So here we calculate the Lennard-Jones potential. This is the formula for the same. The epsilon and the sigma that is given here, we assume it to be 1, so that we can, it is easier for us, but you can obviously include it in when you are doing your calculations. Here we have the setup is in C++, so we have a structure of atom, and the data that comes is from C++, which is what usually people have as a setup for their analysis. And here we have two Python functions, one that calculates the Lennard-Jones potential, and the other one which calculates the distance between two atoms. And we have a third, these two are number jittered. We have a third which sends in the individual atoms to the functions and the distance. And this one, if you see in the number examples, it is jittered, but in our case, we haven't jittered it because currently the jitting doesn't work with vectors, but we are working on it, and we will add that support soon. So as you can see, we can calculate the potential, but of course, this potential doesn't mean much because the values are really arbitrary. So, but this only proves that we can carry out analysis in this form. Next up, we use the extension with pyroot. So we again have to import cppyy.number extension for pyroot. Also, we use the T-Lawrence vector class from root. It has 4 properties, the momentum in the 3 dimensions and energy. It also provides transverse momentum that it calculates on its own, but even users can calculate it by using this formula. And we use this formula to calculate it on the Python side, and then we compare against the PT that we get from C++ to show that the accuracy of the calculation remains the same. So we basically create a vector of T-Lawrence vector and fill it up with random values. And now we have 2 functions, actually 2 pipelines. One pipeline uses pure Python to calculate the PT, and the other one uses number jittered function to calculate the PT. The first, these are feeder functions that again feed the T-Lawrence vector to the function so that it can calculate the PT. And again, as done before, we calculate the warm-up time and the elapsed time. So here the warm-up time is significantly less because the function that we are jitting is very small. And as you can see, for pure Python, we take about 0.007 seconds, whereas for number, we take about 21x, we are 21x faster for it. And I've also printed out 3 sample values to compare visually, but since there are a lot of other values, I have used a computationally method to compare them. And as you can see, all values indeed match. So showing that we are accurate both in Python as well as C++. Moving on to RDF, you can also use this in RDF using root number declare. So root number declare was introduced so that Python can be used inside RDF. And now you can use pyroot inside the Python that is used for RDF. And it comes a whole circle. Here we just show some sample values such as 2 to the power of 3, 4 to the power of 5. And we also pass an RDF through a power function. And as you can see, it gives you the all elements to the power of 3 as it should. Now, finally, I would like to talk about the future work that we want to achieve. So first goal that we want to achieve is to have complete C++ feature support. Currently, the number extension only allows us to work with pyroot functions that return primitive values. We are actively working towards supporting returning of complex objects and reference types. Along with this, we also want to support memory management, constructor support, and virtual inheritance. The second goal that we have is called inlining. So for the code that you saw in calculate PT, we have 2 calls to px and py. And in C++, this would be optimized away by doing memory access. So we access the variable of LV directly instead of calling functions from it. And that is what we want to do at the machine code level as well using number. The third goal is to support GPUs. Number already supports CUDA GPUs, but it doesn't support pyroot objects right now. And we want to support GPUs also in the future. And finally, we want to support automatic parallelization. So OpenMP has these instructions at the machine code level that can be inserted automatically to parallelize the computation. The user just has to specify if he or she wants to parallelize it or not. Finally, to conclude, I would like to say this extension enables use to use pyroot with number. This gives physicists a different way to carry out their analysis. For loops are not to be seen as something that is very slow anymore. And it is very easy to use. You can just import cppyy.number to use C++ in number. It makes Python code faster while keeping debugging easy. So all debugging features that are available to number users, which are a lot, are still available and with the extension enabled, and it makes it easy for users to debug number code. So how do you use it? So currently the PR for the pyroot extension is open and will soon be merged into root master. Until then, you can try out the notebook in the repo that I have created for PyHEP. It is also linked to the timetable. That's all from my side. Thank you.
Thanks so much, Baidyanath. That was really interesting. So we have some minutes for questions. If people have any. There aren't any in Slido at the moment. Guess you can. Oh, yeah, okay. Jim has asked one. He's wondering, how is this related to efforts to include number in our data frame?
Yeah, this is also related to that because I mean, our data frame already uses number in the sense that this number declare function uses call func in number to call to make this Python function into a C function and then you are basically calling a C function that is created from Python function here. So I guess it's like a full cycle now. You just you can use C++ inside the inside the Python function, and then it will get converted into a C function using number declare.
Okay, but this is a separate implementation. This is these are two ways of going about it that do slightly different things, right? It's not that one of them.
Which, I mean, I'm not sure which one you're referring to. So if you can explain that, I'll
like the
answer.
root number declare that's using a number function in our data frame. What you've developed here is distinct from that. That was my
yes,
question.
it is distinct from that, but it also, so this is also one of the goals that like whatever we can use in like if we whatever we are using in number will be automatically be supported by this, because this is also cfunc related. So it's I'm not sure exactly what you are looking for in number with RDF. If you can tell me that, I'll tell you, but this is basically is the efforts that are going into it.
Okay, thanks. That's an interesting discussion there. And Eduardo, do you want to ask?
Yeah, quick question. My usual question: are you discussing or in touch with any say physicist analysts to see how this is attractive for them, or how they would use it? What would be in practice the benefits and stuff like that? Or this is for the moment purely, say, quote unquote mechanical work?
I mean, it is a bit mechanical. We are trying to release it in PyRoot. It is already released in CPPYY, so people can try it out. And once they try it out, they can. I mean, that's why I think I'm also presenting it here, so that people can know about it. They can try it out and give us more ways that they want it to evolve.
Of course. Okay. Thank you.
Yeah, that's very interesting, and I hope that people take you up on that. That potential users can have a look at it and feedback to you how much they like it and what improvements might need to be made as well to make it as useful as possible.
Yes.
I don't see any other questions, so thank you very much, Baidyanath, again. And in fact, thank you to all of the speakers in this first half of the session. And we can now take a break for 33 minutes, I think. So there's plenty of time to go away and make yourself a cup of tea or get a juice. And we will resume at 16:30 CERN time. You can make your own time zone transformation there to know what time to come back in your local time. So thanks again, everyone, and we'll speak to you soon. Bye-bye.
Okay, hello everyone. I hope everyone can hear me right.
Yeah, we can hear you.
Perfect. So that means I can start this last session of this year's PyHEP workshop. So our first contribution, we will have Jonas, who is going to talk about setfit and how to do bin fits and histograms with it.
Hi, do you hear me?
I can hear you, so please go ahead.
Good. And let me just share my screen. I think you see my screen now.
Yes.
Good. All right, then welcome everyone. My name is Jonas and I'm going to talk about setfit and how we can extend this now to do actually bin fits with it. So a brief history on what is setfit for anyone who doesn't know. I will first introduce it a bit and talk about unbin fits to get you a basic idea what it is about, and then we swap to the bin parts. So a few years ago, we all know that analysis started to transition from C++ to Python. PyHEP was created, and we tried to create these many small packages. But one of the clearly missing parts was still fitting packages, which were mostly in C++. And there were a few smaller scattered packages, but they all lacked a bit something. So basically, we looked around a bit more systematically and just didn't find anything that was suitable for model fitting in hydrogen physics. And that's how setfit came about. We thought there are three things we need in HEP to be flexible and have advanced features. We need to be scalable for large data and complex models. And it, of course, needs to be Pythonic, integrated into the Python ecosystem. And this is very much what setfit as an idea is. It's combining, on one hand, a well-defined API and the workflow as a basic idea. And on the other hand, it uses computing backends like TensorFlow, and in the future probably checks, that heavily speed up the computation by chitting things and by using automatic gradients. This means that Pythonic, when we say that, and what it means to be integrated in the Python ecosystem, that's, let's say, the Python ecosystem as it maybe looks like a bit from the setfit perspective. It's built on top of many of the PyHEP packages. It's affiliated with PyHEP, so there is back and forth. But there are also other packages that extend it, like ComputWA can be used, or HEPstats that is built on top, and so on. The goal of setfit is to have a stable core package, which is meant to do model fitting and sampling from these models. The basic idea, and you will see that throughout the tutorials, we will go to some more hands-on stuff soon, is that setfit has 5 independent parts: building your model, your data, creating a loss out of them, minimizing it, and getting a result. With that, the fit always looks a bit the same, but that's exactly the goal of it. So this is a simple fit. We will have this in an introduction tutorial, but it will always look very similar. This is now an unbin fit, but we'll go to the bin fit very soon. Now, one thing ahead, setfit has a strong model building part. And so it contains a lot of models like some product convolutions, Gaussians, and whatever not. However, it is also clear that all these models, I'm saying that because we won't really go into this part of it, like how to create your own models, because we know that high entropy physics needs more than good out of the box functions. And so one thing in setfit is that you can build custom PDFs. Super easily, you can give an arbitrary shape, and the PDF then will function as a setfit PDF and will go fully into the workflow. It has all the things that a PDF has. Integrate sample and PDF, we'll see that. And we can make it like extremely complicated. Arbitrary shapes. And one example is also if you want to use CompWA to do amplitude analysis with SetFit or anything else, this always works. So we will go through tutorials now, but keep in mind that whenever we have a model, this is maybe just a Gaussian or an exponential, but it can also be a few thousand lines of Python code that actually describe your models, and it's automatically normalized and everything. So going to the introduction, you find the links also on PyHEP site to the binder notebooks, so you can directly follow it. This is basically the workflow of SetFit and refers to some imports, obviously. And as I mentioned, there are 5 parts. I will go through this rather fast because I think some people already know it, but there is more information there. So if you're not familiar yet or want to know a bit more, then please go ahead and see these links. The basic idea though is data just wraps data, and this should be actually pre-processed by something else like pandas or hist or whatever, and then you just put the data in. So that's not very spectacular. All we're saying here is we define what is the observable and from where to where does it go. This is some warnings from TensorFlow, but that's very normal. If you start the thing, it says it doesn't find a GPU, that's perfectly fine. And then what we can do is we can create some random data from a NumPy normal, and we have SetFit data set. Super simple. It has a few nice attributes, but that's not very interesting now. So building a model. That's, as mentioned before, probably the strongest part of SetFit. Models in SetFit are mainly PDFs that are normalized over a certain normalization range, also called norm. And they are parameterized by parameters that can later on be fit. Creating a parameter is rather straightforward, I guess. And now we can actually create one of the predefined PDFs, a Gaussian, by saying what are the observables, which is the same as in the data. They, of course, need to match. And we can say what are the parameters. PDF can give us some information about what it is normalized about and everything. And what parameters it has. We use this parameter, sigma is this. We can also have simultaneous fits and multiple parameters and parameters depending on each other. So this is maybe not so clear that every parameter is just one simple free parameter, let's say. And with this, we can get all the free ones. So PDFs or SetFit models, they offer some out-of-the-box functionality, whether you make them for yourself, whether they're predefined or anything, doesn't matter. Namely, they have a PDF function, which is the normalized function that takes a norm argument. It has an integrate method that integrates over a certain range, also multidimensional. Also, if you didn't define integral, it does numerically, and it has a sample. These are basically the core parts. There is actually also an extended PDF and extended integrate, which just scales by the yield if you make the whole PDF extended. So the integration goes like that, and we get a value back. What's maybe a bit surprising is that we get something like a TF tensor, but that's something that you don't need to worry about because TF tensors or checks arrays or whatever, they're all NumPy-like structures. So for most cases, you can just treat them, as you see here, MB square root, as if they were actually NumPy. Or otherwise, you could also just explicitly convert them by something like MB.array, and then you get it explicitly, but that's usually not needed. As said, we can sample from it, get the values out. Sample is like a data object, nothing special. So as you see here, we get the NumPy-like values out, so you cannot just sample and use SetFit as a sample PDF. It has an accept rejects algorithm, so it will be sampling any of your PDFs. And we can use PDF. With this interface, you can also simply do plotting using matplotlib. And we can have a lot of different models in. crystal ball, polynomials, kernel density estimations, conditional PDFs, and so on. But you can also add your own whenever you want. It's quite simple to do. So for a shape fit, what we would do is we can create, for example, a crystal ball, we can create an exponential PDF, and we can create a KDE as a PDF from some simulation. Then we can use some PDF to compose it. We can either use fractions to compose it and set these values, sample from it and plot it. Again, this is all kind of standard introduction, so this is a bit faster. This is now our model, the data. We can also make it a bit more sophisticated and just plot all of the components of our model. So we see how that goes, and we see the exponential, we see the kernel density estimation, and we see our signal contribution here. That's all there is. We just made a. We can do the same thing extended, which just means that PDF has a yield, and when we sum these PDFs, the sum of it will also be extended. Nothing special about it. Then we have loss functions. Loss functions are usually likelihoods or also chi-square functions, which are either like that unbind NLL, or there is extended loss and extended non-unbind LLL if you want to take the size of the data sample into account. Then for the minimization, we can create a minimizer. There are a few available, mainly Minuit seems to be the best one. There is SciPy that is kind of wrapped, and some others kind of locked. And it's actually, side note, even fully compatible with iMinute, so you can even invoke iMinute directly if you want. And then when we have our minimizer, we can just say minimize, and we're getting our result, and we can now plot our PDF. And then it's gonna show us the result of it. There we go. We can look at the fit result, which is going to give us information about different things. We can see the parameters, and we can do some simple uncertainty estimation. We can even get actually minute out that was used. And we can do some simple Hessian uncertainty estimation, or we can do some errors like minus, and then they will be remembered in the result. This is where SetFit ends. When we went through everything, and this is where other libraries can again take over. We can make plots, or we can do statistical inference. And that's where, for example, HEPstats comes into play, which can calculate confidence intervals or limits or S-plots of your data. It has asymptotic calculators and frequent disk calculators. It's actually a PyHEP project. And with that, we can get different answers on the significance of our values. HEPstats, though, is independent of SetFit. It just uses basically the same interface. All right, that was the introduction of what is SetFit. And these are all unbind fits so far. There is a lot more. You can do simultaneous fits. You can do toys with it. You can combine models with products and convolutions and everything. If you're interested in that, go to SetFit tutorials. The link is on PyHEP at contribution, and you can play around with that. So SetFit bit, that's the actual new part, because before SetFit was just for unbind fits, but obviously this should be able to also handle bind fits. Now, when we say bind fits, there are two ways how people would usually probably look at bind fits. On one hand, we can have an analytic shape, and instead of fitting that unbind to data, we can just bind this analytic shape and fit that, which is more, let's say, an LHCb use case, for example. While another way of bind fits is template fits. That's more a CMS and Atlas or semi-leptonics and LHCb use case. which often is also done using the HIST factory model implemented in PyHEP. Now, the HIST factory model is if you have a very specific kind, let's say, of templates, and it's kind of very limited, it has some strong assumptions. However, HIST factory also solves the large use cases of CMS and Atlas. While you can, in principle, reproduce that with SetFit, this is not the goal at all. The goal of SetFit is to be an open world fitter that can just do anything, and especially it should be able to do all the things that you can't do in something like PyHEP. If you do the same as in PyHEP, it's going to be slow and cumbersome and not well tested. So that's what PyHEP is for. We again can import some stuff and go to the binned parts. Now the binned parts in SetFit are analogous to the unbinned PDFs. Often they're just named something like some PDF is now a binned, some PDF. And there are converters back and forth. So to start out, we can see an example, an unbinned example that is just fitting a Gaussian to NumPy array. We create a NumPy array that is normally distributed, variable Gaussian unbinned negative log likelihood, and we fit that. We don't fit it here, but we could do that. This is as we've done before. Now, to go to the binned part, making that thing binned means one way to do it is simply calling to binned and saying how many bins we want. So here we have the unbinned data. We say to binned, and here we get a data object. Then we make our model binned, where we just say we want to have the same binning as data is in. So we could also just give n bins, but let's say just to make sure that we have the same binning as data. And then we can create binned negative log likelihood just to fit a Gaussian. That's all that is needed to create a binned loss, which again, your model can be anything, your data can be anything. All that needs to be done is to binned, and both of them are binned using a binned log likelihood, and we can fit it and get the result. Again, from here, everything looks exactly the same as before. We can do Hesse, we can do errors, all very much the same. And this is then our fit result, as if we do it unbinned, let's say. Now, let's look at this bin part a bit more in detail, because this was a bit shortcut to take. This is the simple way to go about it. Now, what actually happened is that our data object is now binned. Just get a binned space. So if we can compare this and see that ops binned is binned now, and the ops that is not binned is not binned. We also actually see the binning because these spaces have now an attribute binning. That's this one here. That probably looks already quite familiar to some user. Now, this was a simple conversion, but we can do all these steps explicitly. So we can, for example, take our unbinned observable and say this observable with binning, we can give a number of bins and we get the observable binned. Or we can define a binning differently by saying regular binning using this syntax, or a variable binning. This is also supported. This doesn't look by coincidence like HIST axis. This is very well on purpose. We'll just see that. And we can also just create actually a space from the binning, because that already defines everything. So we get this out. Now, if you want to convert data into models, we can now use, for example, this bin variable, this one here, and say, okay, use this now variable binning to binned, and we get bin data set. That looks a bit odd, but we're choosing out variable binning, and we can say model to binned, and we get the same model binned in this variable. So far, straightforward, everything can just be converted with to binned, or also to unbinned if you want to get it back. As you may have already noticed, there are a few things that are very similar to UHI, and that is on purpose. SetFit is, of course, fully compatible with UHI, or as far as it can be. So the bin data object directly adheres to UOHI, and it also has a toHist attribute, so you can directly get a histogram or also a boost histogram out. And bin PDF has directly a to-bin data or a toHist attribute, so you can convert them like this. So if you want to create a histogram, you create a model, analytic one, whatever, you want to have it binned, you do to bind, then you want to get a histogram, then you can do that, and you get your histogram. We'll plot that later on. So bin data has all the attributes that we expect them to have, like values and so on. And binned PDF is basically the same as an unbinned PDF, but it has two more methods, the counts and the relative counts. It still has PDF and extended PDF because that's not quite the same. PDF is the density, while the count is the integral over the density. And the difference is basically the bin width, which with constant binnings is just a constant factor that we need to divide by. With non-uniform binning, that gets a bit more tricky. But this is whenever you try to plot a histogram versus a PDF, that's the factor that's usually missing, because one is density to PDF and the other thing count is the integral over the bins. And we can, as with the unbinned one, we can just sample from it and we get all that. And one of the benefits of this binned interface is that plotting now becomes a lot easier because we have PyHEP. And we can just plot, for example, data. See, this is a bin data and set fit, it directly works, or a model to hist, just scale it correctly, because this is not an extended PDF. And we got this. Or we can use the sample where we sampled from them, that the sample, so it's not exactly an Asimov data set. Or we can also plot the density. So here we use now our model.pdf function to plot the density. And we have data and density true. Oh, we don't need that hist. And we see that the response, we can also just give in X to our model, but because our model is binned, it gives us a binned response. There are also binned loss functions, namely the extended binned, negative local likelihood, and same for chi-square. And we can do something different than just going from unbinned to binned. We can also directly start with the binned histogram. And this means we can create a histogram PDF just from a histogram. This is now actually a histogram. We can give it a yield parameter, and we can say this is extended using this histogram, for example. Then we get it. There are also very few, it's very limited to these template fitting PDFs that help you with modification to incorporate nuisance parameters. For example, there's a binwise scale modifier, which can either automatically create or you can manually create some modifiers. There's now a list of like 50 objects, which are all set to 1 and can freely vary. And the yield is also quite complex, actually. Note, however, that just setting this means just that we're just going to scale the histograms up and down. This doesn't constrain anything. So this is not yet a real Beast and Barlow or something. Another technique that we can use is morphing. We can have multiple simulation templates with different nuisance parameters and then interpolate between all of these. These are different histograms, and we can then use a nuisance parameter and put them into some spline morphing PDF, which we can plot, and we can also make now. We're just using the simpler histogram PDF just for showcase of the fit. We can make a sum of it, which is automatically displayed if you do the toHist. We can sample some data from it, just randomly setting some of the modifiers. And now we can add constraints to it. So we say we have these free modifiers, but we don't want to keep them free. We want to constrain them Gaussian. So we want to say that these bins can vary, but just like Gaussian constraint. And we can create our extended bin NLL. And actually minimize the whole thing, which is now a bit more complicated since we're minimizing something around like 50 parameters. There we go. We have a result of many parameters, and this is in the end the fit result. You can, of course, make things more complicated. And as a last feature to show is that we also can, instead of just converting a histogram to an unbinned PDF, we can, for example, interpolate with it using some splines. So we take our binned histogram, we interpolate, and we'll get this one. Now we plot the new spline PDF compared to the histogram. And now, as typically with setfit, when it ends, we can use hepstats to do inference. Hepstats is now can use these bin fits out of the box, and it can actually also just go ahead and do multidimensional PDFs now. All right, that was the introduction into the bin fits of setfit. So 1 second.
Thanks a lot.
So as a summary, basically where we are now, setfit is also developing, and we got this binned and mixed API now in. The future is we want to clean up things and also change some of the things because there are still a few, let's say, design flaws that are baked in. So we will definitely continue to incorporate also feedback and adapt to other libraries. If you have any comments, any bug things, any ideas, you have an own library that want to get working with it, then please come forward. And the bin fits, they are still rough edges, and there is still a lot of extendability, of course. Yeah, thank you very much. Questions are on Slido.
Yes, so I think we have a few minutes for questions left. So first, thanks a lot for this nice presentation and for filling this gap for using bin models where the hist factory template is not suitable. Maybe I can read out some of the questions on Slido. So the topmost one is about is setfit in any way related to Minwit or iMinwit, as they are both part of scikit-learn, probably meaning scikit-HEP, I think. I mean, is it built on top of Minwit or serves another goal?
Yeah, so the difference is basically they're different libraries clearly, and setfit is to be precise just affiliated with scikit-HEP, but it's very, very close. I think Minwit is mainly a minimizer library. I mean, it provides the whole Minwit, which is used as a minimizer mainly inside setfit. And Minwit has a few cost functions that you can create, but Minwit, for example, doesn't attempt to do model building or anything like that. This is out of scope for Minwit, while setfit has a strong focus of getting this whole workflow with models and everything together. So I would say setfit is mostly using iMinwit.
Yeah, I think.
Yeah, can I comment on this?
Please go ahead.
So, I mean, in principle, you can do all these fits here. I mean, except maybe some that use the special PDFs that only Jonas has. You can also do an iMinwit. Yeah, but on the other hand, yeah, I mean, yeah, like he said. So, I mean, this model building part is not there.
Okay, thanks for this clarification. I think what you also said already answers partially the second question, that is there, which is we use the cost functions in iMinwit or independent implementations, and yeah, is it possible to share more code between the two projects?
Yeah, I mean, I can say this was my question, so because I really think we should collaborate and share a lot of code as much as possible.
So they are actually independent implementations, but you can already share quite a lot because you can use the setfit loss function to minimize with iMinwit. So this is compatible, and also the other way around. You can, as far as I know, also take a iMinwit cost function and minimize with setfit minimizer. So it's just the disadvantage that since iMinwit doesn't provide any models, anything that will depend on a model like doing resampling or something, that won't work then. that needs like some set features. But of course, we I think you would agree on that, Hans. Yeah, we of course try to share and move things, let's say, together or unify and keep this as far compatible as possible.
Yeah, I really think that your cost function should use mine as a backend if possible, but maybe it's not possible because of this TensorFlow backend.
Yeah, exactly. So this is why it's a custom implementation, because it uses TensorFlow as the backend and it's shipped. Yeah.
Okay. I think that clarifies this, and then the last question goes in a similar direction regarding HIST. So does StatFit duplicate the binding API of HIST, or is it using HIST under the hood?
It's currently mostly using HIST under a hood. It's surely adhering to UHI, and it's currently just using the 9 things that HIST provides. It creates a new dependency on it. On the other hand, I think if you want to use anything binned, you will anyway have installed HIST, and this is surely, so there's no need currently to duplicate things. It uses some internal binning stuff because it's also, let's say, the bin data is a lot more limited than HIST, because in the end, it's just for fitting, and it's implemented in some TensorFlow stuff. Some of the operations are missing, and the stuff that you've seen, like axis or the nice plots, that just uses HIST. So it's basically partially using HIST, a bit re-implemented because it doesn't work otherwise. Yeah.
Yeah, but wouldn't it be better just to use HIST objects directly instead of wrapping this again?
And this unfortunately doesn't work, because if you want to tray through with something like TensorFlow, then this doesn't work at all, because you don't have the operations are implemented in C++ behind the scenes in HIST. Boost histogram, right? So it can't go through. Actually, I tried to do that in the beginning and having a backend. So basically what we ended up is just having a bin data object, which has just a very few operations implemented. I mean, most of the operations are not implemented because use HIST if you want to do that. It's more container storage that uses the API of HIST or Boost histogram and uses the functionality of, let's say, plotting, for example, or the axis definition of actually the HIST libraries.
Okay, thanks. Then I think we should move on with our next presentation. So we will have Mason talking about likelihood-based ABCD methods for background estimation and hypothesis testing in PyHEP.
Okay, so hopefully you can see my screen.
Yes.
And hear me? Okay, good. Yes, so the link I'll be using will be this. I'll try running my notebook on Binder. So if it doesn't show up for you, you might have to refresh the Indico agenda. But I'll try running it on here. So yeah, I'll be talking about a package that I've created called ABCD PyHEP. But the package itself is pretty simple. It's pretty small. So I'll spend a decent amount of time explaining all of the other words in my title. And then near the end, I'll actually talk about, once I get through that, then it'll be very easy to show what this package actually does. So should come up in a second here. I'll be talking about this background estimation. That's the main thing, and a particular method for this. If it takes too much longer, I can switch to a local one. Or I guess I can, okay, I can start using the static version here. Yeah, so I'll be talking about this package, but first I'll be talking about background estimation in general. So the first part of the notebook just ignores some warnings that will go away in some future versions. But here I'll start talking about, so I'm really focusing on analyses that are searching for new physics processes. So, so searches for new physics. And in these analyses, the general idea is usually to look for a potential excess of signal-like events above some expected number of events from background processes. And the expectations of what the signal events look like usually come from Monte Carlo simulation. And in a lot of analyses, they also, the distributions that you expect from background events are also provided by Monte Carlo simulation. But in a lot of searches, it's often impractical or impossible to generate Monte Carlo simulations that accurately model the background that's most relevant in the signal-like regions, and or provide enough statistics in order to be useful for analyses with very low background. And this kind of scenario is especially common, like in the cases that I work on for QCD multi-jet background. And so this necessitates the use of data-driven background models, where the background in the signal region is estimated directly from data that is outside the signal region. And so if, without making any further assumptions about the background, you need at least 2 independent discriminant variables in order to do this. And so I'll be looking at an artificial example. I don't know why it's taking so long. Maybe I'll try it, because it was already built. But I'll be using kind of an artificial example where I just generated some example data in Monte Carlo. Let's see if it comes up. And you can see that in the there's another notebook in this repository that I use to just generate some fake data and signal. And then I'll just be loading it here. Well, okay, I can switch to the local version.
Sorry, could you please zoom in the font, the screen?
Yeah. As soon as okay, I'm going to stop sharing and then share a different Firefox window. But then I'll do Binder is unhappy with me. This is the right one. Yeah. Okay. So now you should be seeing the notebook that I'm just running locally. And yeah, I will zoom in. Let's see, probably, hopefully about there is good. Okay. Can you see the note? Is this good for the notebook?
Yeah, that's
okay.
Nice.
Great. Okay, yeah, so sorry about the binder not working. It worked right before. So let me clear the output first. Stop running. Okay, yeah, so I'll load in this, there's a couple CSV files in this repository. So the first one is my fake signal Monte Carlo just generated at random. And so this signal Monte Carlo, I can actually look at it here in the notebook here. So it's just a bunch of pairs of variables. So I'll call the first variable X and the second one Y. And each row just represents an event. And so these are basically my signal-like events in these two variables. So I can visualize this distribution in signal. So just plotting and just doing a 2D histogram. So it looks something like this. So you can see there's like a peak in the signal distribution, and then it just kind of fades out. The density of signal events fades out as you get further away from this peak in the middle. And so as you'd have in a real analysis, generally you have a relatively high statistics example of what this potential signal should look like in data if it exists. So of course, we don't expect to see anywhere near this many signal events in the real data. It'll be scaled down to a much smaller number of events. And I'll also have to deal with the background distribution of events that this signal is hopefully on top of. So then I'll start looking at distribution of the data. So just loading this other distribution in. So here, again, like in kind of a realistic exotics search, we have a lot fewer data points. So this represents, say, all the events in this plane of X and Y, just a scatter plot of all the events that are actually observed. So the question is, how do we know if there are real signal events in this observed distribution or not? And so in order to answer that, we need a method to estimate how many of these events are from background processes. So here I'm assuming that it's intractable to actually produce Monte Carlo to model this background. We have to derive it from the data itself. So arguably the simplest way for estimating background directly from data is called the ABCD method. And so in this method, you introduce a threshold value in each of the two discriminants that you're looking at, and then separates the plane into 4 regions labeled A, B, C, and D. So here I'm just setting this threshold to 1 in both variables, and then I can just make a plot showing this data distribution with these 4 different regions. So A, B, C, and D. And of course, I've designed this in a particular way, but the statement that follows here is true in general. As long as X and Y are statistically independent, it's easy to show with just some integral manipulation that the number of events in region A is approximately equal to the number of events in B times the number of events in C divided by the number of events in D. And it's only an approximation because of finite statistics. So in the infinite PDF limit, assuming these variables really are independent, this is exactly true. So if these number of events in the regions B, C, and D accurately reflect the number of background events in these regions, this formula gives an unbiased estimator of the number of background events in region A that does not rely on any information from region A itself. So this is the kind of object that we want. So the problem comes from what I show in the next plot. So here, so if I show this distribution and the regions for overlaid on top of the signal Monte Carlo simulation, we can see that, okay, region A is really the most signal-like region, most of the signal events in region A, but there's a significant amount of leakage of the signal events into regions B, C, and D. And so if there really are events that we're observing in data in region A, then there are very likely signal events in data in B, C, and D as well. So this breaks the naive method. If we try to use it, we could totally miss an observation of signal in data. And the results will just be wrong in any case. So the correct and much more robust way to handle this scenario is to use the likelihood-based ABCD method. So in this method, we just set up a system of equations. So there's, you have an equation for the number of signal events, or the expected number of signal events in each region. So this is just introducing some variables. So the efficiency of each region normalized to the efficiency of region A. These are all estimated from Monte Carlo, the high statistics Monte Carlo, and then multiplied by mu, which is just a parameter that is allowed to float. It's defined as the number of signal events in data in region A. So this is the parameter of interest, the mu here. This is the signal strength. And then for background, we have the expected number of background events are given by, in each region are given by these equations here. So there's mu B, which is just a normalization of the number of background events in A. And then you have these nuisance parameters, tau B and tau C. And these are just introduced to enforce the standard ABCD relation, this like NB times NC over ND is equal to NA. So this is always true for the background. It's just in data, we have no way of a priori separating the background events and the signal events, if there really are signal events there. And then with the system of equations, we get the total number of expected number of events in each region is just the signal number plus the background number. And so if we set particular values of all these parameters, we can calculate Poisson likelihood based on the expected number of events and the observed number of events in each region. And then at this point, we can perform maximum likelihood fits with these parameters in order to do all the statistical tests that you need in order to get your analysis results. So this is where I come up to the ABCD PyHEP package. So this is a Python package that facilitates doing exactly these statistical tests. So it's fairly narrow in scope. This is not like ZFit or iMinui that's doing, or PyHEP itself, which is a very broad and powerful tools. It's specifically a convenient wrapper around PyHEP that allows you to build the proper PDFs and run hypothesis tests for this likelihood-based ABCD method. So first, to just go through how you can use this package. Okay, so I just defined this function so that I can get the yields out from my signal Monte Carlo and data, just to get the number of events. So then I can look at these individually and see like how many events were observed in each region. I can also look at for the signal Monte Carlo. This is part of the input to the ABCD method. And then I also need the total systematic uncertainty for the analysis. So this is a complicated number that I'm not going to worry about at all because it's the product of many dedicated studies and a real analysis. So I'm just going to say that for this artificial analysis, the systematic uncertainty was calculated to be 10%. So I just set it arbitrarily. So in this package, the main class is just this ABCD class. So this creates an object that carries information about a particular ABCD plane, which includes the yields from signal Monte Carlo and data, as well as this systematic uncertainty. So I pass in this information to make a new ABCD object. So I just import it and then create this object and call it ABCD. And so now I can use this object to do all of my statistical functions. So the lowest level thing that I can do with this object is just extracting the maximum likelihood estimators of the parameters that I was just talking about and their uncertainty based on the data that's been observed. So I can see all the parameters that are in this model by just doing this par names function. So mu is the parameter of interest, the signal strength. Then there's a systematic uncertainty, and then these nuisance parameters that I described earlier. And so I can do a couple different types of fits. So I can do a background only fit where I fix the signal strength to 0, and then it will return. So the first column here are the parameter values. The second column are the uncertainties in each parameter. It's just in the same order as they're listed by par names. And then I can also, so this is for the background only fit. So you can see mu is set to 0 here. And I can also do a fit allowing all the parameters to float so that the signal strength is set to its maximum likelihood estimator. So in this case, you can see the maximum likelihood estimator of the mu is like 12.8-ish. And so, yeah, I just explained that. So basically this is saying that the estimated mu is like 13 plus or minus 9, just going straight from the fit. Let's see. Okay, so I see there's a question on Slido. So from Nikolai, is there a reason for using this particular parameterization? For example, one can probably find a way that produces less correlations between the parameters. This is the standard way that the likelihood-based ABCD method is done in Atlas. So this was kind of set up by the Atlas Statistics Forum. There's certainly correlations between the parameters, but I haven't seen it cause any problems in the analyses that I've used it for. But there are certainly other ways to parameterize it. But this is the way that, at least the standard way to do it within Atlas. Okay, and I think Lucas's comment is or question is more of a comment about whether could some of these, well, okay, so if some of the inference driving stuff could use cabinetry, that is possible. That's something I haven't investigated, but yeah, it's possible. And yeah, exactly. This package adds to the models that are possible, that are kind of implemented without too much overhead in PyHEP, because you can just use this package. Let's see, is there some assumption about signal uncertainty being the same across all regions? Yes, exactly. Yeah, that's a good question. And this is kind of an arbitrary thing. So the reason why it's set to a single number is because the analysis that I wrote this for is doing exactly that, using a single uncertainty for all, systematic uncertainty for all the 4 regions, but there's absolutely no reason why it has to be. And it's a very straightforward extension to make it so that it can be different in the different regions. And that's something that I plan to add. Yeah, it's certainly something that makes sense. It's just it was just the analysis that this was written for. Yeah, just used a single number. Okay, so I'll keep going. So next, you can extract the likelihood values at various parameter values. So there's a function that's just twice NOL. This is coming more or less directly from PyHEP. It's just making this easy to run. So I can just do twice NOL. And then this will give me an array of, by default, it runs it at a variety of signal strengths. So that's what this first array is in here, all the signal strengths that it calculates, twice the negative log likelihood. That's what this is calculating. And then the second array is just the actual values of the twice the negative log likelihood. So these are the values. I can visualize this. I could plot it from that array there, or there's also just a function that's called twice NOL plot that just produces this plot. So here I can see that, okay, the negative log likelihood is minimized at this is the maximum likelihood estimator around 13. But a value of 0 certainly can't be excluded. This is, within a couple sigma, certainly. I can actually say, I didn't put it in here, but the way that I generated this fake data was it's actually a background plus an injected signal with a strength around 6. So we can see that's the real underlying mu value is well within the uncertainty here. So there's really, I think, 6 signal events in region A. And then we can do so what are called CLS tests. So the values like CLB, CLS plus B, and CLS, these are values that are used, at least by the LHC experiments, for discovery and setting upper limits on signal strength. And so there's this reference here that's used for a lot of PyHEP, and you can also see it for, it mentions some of how CLS is used if you're not familiar. So I won't try to describe the CLS method here, but just a note that you can get all of these values. So I can get the CLB values. So this is the same kind of format as the twice NOL. You get the mu values, the signal strengths, and then the corresponding CLB values, and then the same for the CLS plus B values. And then what we really generally care about the most for in terms of getting final analysis results in terms of discovery or setting upper limits on a particular signal is CLS. So if I run this CLS function, so again, I get all of the signal strengths array, then I get the observed CLS values, and then the expected band, which is the median value of CLS, assuming that the true value of mu is 0. And then that median value plus or minus 1 sigma, and also plus or minus 2 sigma. So it's a lot of numbers. It's easier to visualize in terms of what we often call a Brazil plot. So this is another function that's just implemented without having to put in all the parameters in the right places. It'll just automatically create this plot for you that shows, that scans across the different mu parameter of interest values, and then shows the observed CLS values, the expected CLS, and then the green is the plus or minus 1 sigma, and then the yellow is the plus or minus 2 sigma. And then in terms of the final results. So here we see that basically the observed values are within, in all cases, it's within the 2 sigma band. So we certainly wouldn't be able to claim any kind of discovery here. But so we would set upper limits on the signal strength. And so usually we'd be setting an upper limit at a 95% confidence level. And so that would be where these lines intersect 0.05. So that's this red line here. And then there's another function that just extracts those values. That's just called upper limit. So if I do upper limit, then I get the observed upper limit is the first number. So this is where the solid black line intersects the red. And then the expected upper limit band, which is where all the other lines intersect this red line. So the observed upper limit is like 30. The expected was closer to like 19.5. So we can see this upper limit is a little bit more than more than a 1 sigma deviation. So it's an indication that maybe there's signal there. And in this case, because it was set up in an artificial way, I know that there really is signal there. So if we collected more data, increased the statistics, eventually this would become significant. And at some point we discover the signal, hopefully. Okay, so that's kind of the end of just showing how this fairly simple little package works. So just in summary, the ABCD method is one of the simplest and most common data-driven background estimation methods. To be more pedantic, it's really a family of many methods that use very similar techniques. You can use more regions, you can arrange them in a more complicated way, but almost all of the methods that are actually used in modern analyses are some variant of the likelihood-based method described here. And so this package, ABCD PyHF, is a small pure Python package that only depends on NumPy, Matplotlib, PyHF. So there's no dependence on any experiment-specific formats or code, even though this was developed for an Atlas analysis originally, but it's all on GitHub, it's open source, it's public, and there's nothing Atlas specific about it. So basically for any experiment that is interested in using this kind of method, any analysis, this works out of the box for most simple cases, and it's intended to be extensible to accommodate more complicated cases. So if you have something that doesn't fit into the box that this package currently provides, then please let me know, or contact me, or make a GitHub issue or something. I'm using this for my own Atlas analysis right now, and an early version of this was used for analysis that was already published. And there are a few other Atlas analyses now that are also using this, or at least trying out this package to see if it can simplify their workflow. And then I just added a few links at the bottom for the GitHub repository for the actual package. It's on PyPy. You can just do pip install ABCD PyHF. There's also an ACAT poster from last year. Let's see if there are any more questions. I see another one from Lucas. Is there some affordances in which these ABCD regions can be included into a larger likelihood? I think so. That's kind of what I was getting at when I said here about the extensibility. So I think I'm designing this in a way that I think that it should be fairly straightforward to extend this to include more regions or part of a larger likelihood. But yeah, that's definitely something that I'm considering. There's another question. Is the interface extendable to higher dimensions? That's another. So it depends on exactly. If you still have the same number of regions, you can use this no matter how many dimensions you're cutting in. But you probably mean, like, the more common scenario would probably be where you have more regions. And that's again something where I think the extension is fairly straightforward. It hasn't been implemented, but I've seen some analyses that would be interested in using something like this, but use more regions. So that's again something that I'm investigating, and I think would hopefully be not too difficult.
Okay. Yeah, thanks a lot. Perfect on time. Currently, I don't see any other questions on Slido, but yeah, please feel free to continue the discussion on Slack. And yeah, thanks again for presenting this really nice package. I think it's really great to have these kind of commonly used methods in places also where one can figure out all the details. That simplifies really a lot of things and avoids mistakes that people could make. Okay, then the next presentation will be on a related topic, also about PyHF fits, and that's about a PyHF to combine converter by PyHEP. So I can see your slides. Please go ahead when you're ready. We are currently still muted.
Can you hear me now?
Yes, I can hear you.
Okay. Let me go back. Okay. So my name is Peter Ridolfi. I'm the author of this PyHEP to combine converter software. First off, I just want to give a thank you to the PyHEP organizers for allowing me to present on this, and a special thanks to Dr. Alexander Held and Dr. Matthew Fikert for mentoring me through this project and making it a success. So first off, just in general, if you're not familiar with PyHEP or Combine, they're basically just statistical tools that allow us to perform analysis on the data that's collected in the ATLAS and CMS experiments, respectively, that are done in the Large Hadron Collider. There are some differences. So PyHEP is more kind of lightweight than Combine, so it's easier to use, faster, and more efficient. It kind of has less. It has less of the nuances that Combine offers. Combine offers many user options that allow for deeper analysis into data. But people that are familiar with PyHEP or people that are familiar with Combine don't really know how to use the other one. They're not really trained in the other model. So the motivation behind this translation is to allow for somebody who's not familiar with either one to just simply translate a model and being able to take advantage of these nuances. So the overview of the project, obviously we want to have a bidirectional translation between PyHEP and Combine. That involves, first, there's different formats for the specifications of the model. So PyHEP uses something called his factory JSON specifications. And then Combine uses text specifications, which they call a data card. In both cases, the specifications for the models are based in histograms and counts. So the translation is relatively straightforward, but there are some obstacles such as the uncertainties and the way the histograms are presented are slightly different between the two. So that kind of presents itself as an issue in the translation. And also, especially going from Combine to PyHEP, some of the extra things that Combine offers are not offered in PyHEP. So that also has to be handled in the translation. So here's some workspace examples. On the left, we have a simple Combine model, which has your channel samples and uncertainty modifier. And then the same model on the right is in PyHEP, the JSON format. Again, we have your channel, your signal, your modifiers. So with running the translation, it's designed to be run where you can take advantage of both the Combine and PyHEP tools. That makes the translation easier. The way that it's meant to be run is in a Docker container, because that's really the easiest way to install the Combine commands. And then also it's easy to install the PyHEP commands alongside that. And then once you have the Docker container running, the instructions to do that is on the GitHub page that's linked in my talk and in this PowerPoint as well. Then you can run it from a command line interface. Depending on which direction of the translation you're going, you only need the file for the specification, JSON or the data card based on, whether you're going PyHEP or Combine. Also, if you're going from Combine to PyHEP, the shapes for the histograms are separate in Combine. So you need to include the shapes file in the directory that you're doing the translation in so that the computer can actually read those histograms. So the translation for PyHEP to combine, first we need to parse through the JSON model and take all that information and translate it into an object that is called the data card object. And that was just written by Combine. And basically it just has a bunch of the information that you need for your model. And then after that's populated, we need to manually write the data card file in a text format because there's not a function to do that currently. And also we need to generate histograms and put them in the separate shapes root file because in PyHEP, the binning is just built into the model specifications and in Combine it's separated. So we have to create that separate file. And also in Combine, samples that are signal are designated with negative numbers and then background is with positive numbers. And so we have to decide which samples are signal in PyHEP based on the presence of signal strength modifiers and not based on the numbers so that we can specify that in Combine. For PyHEP or for Combine to PyHEP, we take this data card parser thing and we create a data card object and that basically parses through the text file automatically for us. And then we can create the object, which we can then take all those attributes and build the JSON specification from scratch. We need to read the histograms that are separate and combine and I use uproot to do this. And then we can put all of that data into the JSON file together with everything else. We also need, since PyHEP only identifies signal based on the presence of modifiers, signal strength modifiers, which are called norm factors, we need to read which samples are signal and add norm factors to every sample in the JSON specification that is a signal. And additionally, some combined systematics like log uniform are not supported in PyHEP. Like I said earlier, Combine has a lot of extra bells and whistles that PyHEP doesn't offer. So this needs to be accounted for and an error must be raised so that the user knows the translation is not going to be accurate. So some important differences here. PyHEP has uncertainty modifiers that are called stat error and shapesys, and they're basically these global uncertainties. And Combine also offers these. It's called AutoMC stats in Combine. But the fits need to be kind of converted before you compare them because the values are handled differently in PyHEP versus Combine. So in PyHEP, these values are centered at 1, and then that value is directly multiplied by the nominal value. In Combine, it's centered at 0. So then this is like added to the nominal value. So there's just a translation that needs to occur there. Combine also implements something called a shape normalization split, and PyHEP does not do this. So automatically in Combine in a data card, if you have a uncertainty that is a shape uncertainty, which means it's just a histogram with different counts, different yields than the nominal value, Combine will automatically create a normalization factor that will change those yields based on how many more or how many less it has than the nominal histogram. So when you're converting from Combine to PyHEP, you need to manually add in this normalization factor into the PyHEP workspace. If you're going from PyHEP to Combine and you don't have this normalization factor, you just need to turn off this automatic generation in Combine. The last thing we need to do with the translation is validate that it actually works. So I generated these likelihood plots for models that were converted. And although there was a lot of speed bumps in creating these plots, eventually I was able to get them to perfectly match. So that validated that the translation was working. And also I generated the expected yields in both models and they also matched. And finally, I did a round trip translation. So I went from PyHEP to Combine, back to PyHEP, and the specifications for the two PyHEP models did indeed match, further validating the translation. Finally, I did the translation for a realistic size model, and I proved that the fits for the values were in agreement within 1%. And I generated polls for these fits, but in PyHEP, the polls are slightly greater than combine. And I have a feeling that that's attributed to the fact that the prefit values in combine are like pre-calculated and are kind of closer to the actual fit values than in PyHEP, where it's just a 0 or a 1. And this kind of disagreement needs to be further looked at. But that is my best guess of the reason for that. Final closing remarks. The success of this project is really big for high energy physics in general, because now people are able to take advantage of both the advantages of PyHEP and combine without knowing how to use one or the other. And anybody can do this. The script is currently available on GitHub for public use at this link. And also it's available as a package on PyPI. So you just need to do pip install PyHEP combine converter, and you'll be all set to go. Thank you guys for listening. I think we're out of time for questions, but yet again, I appreciate you allowing me to present. Thank you.
Yeah, thanks a lot. Sounds like really a great tool. Yeah, maybe I can squeeze my question in for the last minute. So are you planning to also use this to publish likelihood? So PyHEP has this nice JSON format for CMS analysis.
I can maybe jump in and kind of comment there. So I don't think that CMS is going to directly just take these converted models and publish right away, but I think that this is definitely hopefully a stepping stone towards getting to the point where any LHC experiment that wants to publish full statistical models to HEP data can. So I'll let CMS people speak for themselves here, but I don't think that this is going to be a one and done sort of situation. But we're looking forward to trying to help facilitate things.
Have you been in touch with some CMS people on that? So Nick Wardle and so on, they had like a CMS internal meeting on publishing likelihoods, and they were also interested in this type of converter.
Yeah, I need to talk with Nick again. I know that I know the meeting you're talking about, and so I think that there's interest there, but I don't know if they're at the point where they can say like, okay, this is good enough, but we should definitely follow up.
Okay, that sounds like a good perspective. I suggest we continue with the next presentation on scalable and sparse I/O with LarkV from Corey.
Good morning. Can you hear me okay?
Yes.
All right, I'm going to share my screen. Okay, hopefully you can see my slides. So good morning, everyone from Chicago. Good evening if you're in Europe. I'm going to talk to you about a software package we've written. We call it LarCV. The name came from Liquid Argon Computer Vision, so that CV is kind of harkening back to OpenCV namings. Oops. So I'm going to start with the why of this project. Maybe you've heard of this thing called machine learning and deep learning. Seems pretty cool. There was, some general consensus that if you could mix and match deep learning and high energy physics data, you could maybe get better science. I don't think this is a controversial opinion in this meeting, but I'll point out that this big plus sign is not always obvious from a computational perspective. A lot of these deep learning techniques are coming from big image analyses or text processing, and the data we process in physics is not always that. The challenge that we were facing in the neutrino world is that our data doesn't look like that image data. Typically, we have either really massive sparse images or something in 3D or point clouds or something like that. And the degree of sparsity can sometimes be incredible, less than 1% or 0.1% of voxels filled. And each example that you want to look at has a different degree of sparsity, so you don't have regular data. That's not an unfamiliar problem to this audience, but the challenge that we were facing is when you want to scale out and use, say, a supercomputer to train your model, sparse and irregular I/O is not a trivial pattern to manage, and it can become a bottleneck, especially at larger sizes. And you could just voxelize everything as dense data and compress it, but that turns out to be slow at scale too. Just to give you a sense of the data that this was built for, this is from one of the data sets. It's from the short baseline near detector at Fermilab. This is called a cosmic tagger data set. It's just doing a segmentation task. But the background pixels in this, shown in gray on the right, are about 0.1 to 1% of each image. And the actual red target pixels are typically less than 0.1%. So the solution that we prepared, that we called LARCV, fills this niche where you can take this data and get it to all of your accelerators on a supercomputer with low latency and at scale, so massive numbers of GPUs at a time, 2,000 or more. We wrote this package half in C++ and half in Python with bindings from PyBind 11. The approach we were going for there is dealing with a simulation package that isn't very accessible from Python and very slow from Python. So it helps to be able to pull data out of the simulation in C++, but have the same interface on both sides so that you can actually use Python when you want to do the cool machine learning stuff. And we wanted scalability and performance kind of by design. So we're not trying to hit speed records for I/O, but you need to stay fast. And one of my earliest physics professors always pointed out that, when you use a term like fast, it should be compared to what? So fast here means compared to however long it takes the rest of your algorithm on a GPU. So if your I/O is faster than that, you're going to be not noticing it. And we built this whole thing on open source and HPC friendly and Python friendly tools. So, NumPy, HDF5, CMake, and C++ via PyBind 11. And that's pretty much it. The GitHub link is there. You could also click the link in this, the PyHEP Indico page for the read the docs page and find the source code. The real thing that we developed was basically a data model for custom I/O layers. It looks similar to SQL, so it's basically turning your sparse data into tabular data. And instead of giant, 1,000 by 1,000 image reads of I/O, you're doing a small tabular lookup that you can parallelize with HDF5. And you don't have to know any of this to use the package. The user code is meant to be really kind of familiar looking and easy to use. Just some example data sets that I'll flash by. The data looks like this. We can store lots of different things that are useful for machine learning. Like here is an image with bounding boxes laid over it. Here's the same image, but looking at instance segmentation labels. So if you wanted to do clustering with machine learning, we can feed that data. And again, in 3D, image on the left is segmentation label bounding boxes versus the source voxels on the right. One of the advantages that we get from LARCV is basically I/O performance. Compression is cheaper in sparse data compared to dense data, even for the same data sets, and even using all the best compression tools. And because we use so much sparse data, we've added some basic, simple sparse manipulation tools, cropping, resizing, augmentation as you load it. And the user interface is the object level, so you don't really need to worry about all these storage details. And the under the hood layer written in C and HDF5 easily supports MPI. So when you want to go up to massive scales for readback, it's no problem. We did a couple performance studies. I took a couple data sets from neutrino physics. They're just listed here. You can see the occupancy, this right column is typically 10 to the -3 to 10 to the -6 for these data sets. That's how many voxels are filled out of how many voxels per image. So how many non-zero ones. It's typically very sparse. And we see that just going from reading back dense data to a dense array versus sparse data to a sparse array, like if you were going to feed it into a graph convolutional network, there's a 50 to 60% improvement in I/O throughput. And it holds up as you scale up your mini batch size too. So your throughput really doesn't drop off as you get to bigger and bigger batches. And we also have a concurrency layer built in. So a lot of the data loaders in PyTorch, for example, use multiprocessing to pull up the next batch of data while you're using your current batch of data. LARCV does this too. It's built on STD futures. So once your data is loaded and processing on the GPU, the next data is getting ready. So I've run this on one of our latest supercomputers. Even at 2048 GPUs, I/O latency was about 10 to 20 milliseconds. And it scales out as well, as I mentioned. So this is going up past 10 to the 4 MPI ranks. You can see for all 3 of the data sets benchmarked, the throughput compared to the single node performance is basically linear with a few quirks. Notably, this supercomputer was bigger than one of the data sets in terms of total number of ranks. So as I got through a couple iterations of the data set, HDF5 caching kicked in, and I actually got a throughput speed up above a certain range. And in the biggest run we did, someone else stalled out the supercomputer and it took 20 times the standard time. So there's 1 point that dropped down. Is it useful to you, and is it stable and ready to go? I know all the developers here will admit that no project is ever quite finished to your own satisfaction, but you can't let perfection ruin progress. So LarsCV is ready for general use and stable for several years. There are features considered for future upgrades like point cloud data sets and direct to GPU loading, as well as integration with some of the framework data loaders to make it even easier for use. And just kind of as a summary, we have several developers led by Argonne National Lab, and we have a sparse data I/O format. So if you want to use your weird and sparse data on supercomputing clusters and not have I/O be a bottleneck, LarsCV might be useful for you. If you already have a solution, obviously, if it ain't broke, don't fix it. Some of our notable features is just the sparse data manipulation, concurrency with GPU processing, and really good weak scaling. So, more than 16,000 ranks and global batch sizes of more than 250,000 sparse images took just 20 milliseconds. So things that were unmanageable before in dense format, particularly in 3D, are now manageable using this package. So thank you. Happy to take any questions.
Yeah, thanks a lot. That sounds very interesting. And I think maybe partially my question is already answered, but yeah, my question would be a bit how does this compare to awkward array and also to graph neural network libraries? So mainly what's the additional thing it can do that those can't?
Yeah, so I'm not a user of awkward array, and I can't really speak to the pros and cons of various ones. So if you have a workflow in awkward array that's working for you, awesome, go for it. One of the things that this offers is it's generally built with supercomputers in mind. So everything is built to be scalable. I don't know how scalable awkward array is, but you can take LarsCV and go run it on Summit or Frontier or Polaris or Aurora next year, and it will work up to the scale of the biggest supercomputers that are out there. Does that answer your question?
Yeah, maybe a bit. And I think what maybe there's also a point. These sparse to dense operations. When I tried to do this, was usually a little bit manual to do that. When you have some kind of sparse or checked representation, and then need to put it back into a dense one in an efficient way, that usually was a bit cumbersome.
That's all built in here. You can always go from sparse to dense and from dense to sparse here.
Okay. Yeah, sounds very, very interesting. Thanks a lot.
Yep, thanks.
Then I think we can move on to the next presentation, or the actually last one for today and for this workshop, which is about the ChatNet library for machine learning and high energy physics by Rakhav.
Hello, can you hear me?
Yes, I can hear you.
Okay, and can you see my screen?
Yes.
Okay, great. Yeah, hi everyone. I'm Raghav. I'm a PhD student at UC San Diego, currently at CERN with the CMS experiment. I'm very excited to talk today about this library we've been developing called JetNet for developing and reproducing machine learning projects in high energy physics. So a similar area as the last talk. And thank you to all the organizers for this amazing workshop. I've learned about a lot of really cool tools I'm excited to use. I'll talk about one, which we're developing. And so just to introduce this, I'll start with maybe the problems it's intending to solve. So as Corey nicely introduced, machine learning is really becoming ubiquitous in HEP for a lot of different applications, classification, reconstruction, simulation, and so forth. And so we are basically trying to help people who want to get started and try to actually use machine learning in this field, and particularly those who may not already be very familiar with the data sets and the ecosystem right now to do this kind of research. So those who are coming out of the field, for example, or who just aren't, keeping up to date with the latest file formats and how data is represented. And so it's designed to make it easy to get started with this kind of research and focus on actually the model building and training rather than dealing with data and metrics and so forth. And so it's a way to get started. It's a way to have easy metrics to evaluate your results, standardized, and also allows us as a collaboration and as a community to be able to reproduce and compare results between different models and projects. And JetNet is a solution to these problems, or potential solution with easy to access data sets, standardized metrics, and more utilities to ultimately improve accessibility and reproducibility in this area. And just as a disclaimer, this is still mostly just starting out as a project with currently a limited number of data sets and metrics. And any feedback or contributions to improve this are very welcome. Right. So today I'll just go over some very simple things you can do with this library, which is to load one of the data sets included, and to just look at it and visualize it using some of the utilities, and then finally actually prepare the data set by using a PyTorch data class and in preparation for training a model. And so just to start with, we can just import one of the data sets which we want to use. So here I'm choosing JetNet just because it's the smallest and easiest to work with. So we can import this, and before trying to load anything, we can just look at the features available for the particles and the jets. And I should mention right now the data sets are all point cloud based data sets for jets. But again, one of the things I'd like to emphasize is if there are features or data sets or anything which you want to be able to use with this library, we're very open to any requests or contributions. So we can import this and just print out the features available. So the 3 kinematic and mask features for the particles. And this jet type, kinematic features, and number of particles is available for overall jet features. And then we can, looking at this, actually load the data directly by calling this getData function and feeding in these arguments. So we can specify the jet types we want. So JetNet allows us to specify, the specific types of particles which produce a jet, the data set directory, and we can select which particle features we want to use if we only want the subset, for example. So here selecting just the kinematic features, the number of particles we want per jet, and selecting a subset of jet features. And so we can run that and load the data. If you're following along, it'll actually download the data set for you. I already downloaded this here just to speed up the demo, but it's a pretty small file, so it shouldn't be too long. And then we can print out some of the data and just look at it directly. So we can see I'm printing the 10 highest momentum particles and their 3 features, and the jet features which we asked for are shown here. Right. And instead of looking at it just directly, we can visualize these jets as images. So using this toImage function in this library, I won't go over all the plotting code, just showing that we can pass our data, this particle data, into the toImage function, and we can get out of it these jet images, basically visualizing the gluon jets, the more complex top quark jets and W boson jets. And we can also use this other utility to calculate overall jet features just from the particle constituents and plot those. So we're feeding in the particle data into this jet features function, which is actually using awkward array under the hood, and extract the mass and plot it here. And so we see that everything is as we expect for the gluon jets, the top quark jets with the top and the non-fully merged jet peaks and the W boson jets. Right, so this is just show a very easy way to load the data. So the point is that we shouldn't really have to worry about messing around with data. We can just do this quickly with almost a single line of code and move on to actually training our model. And for training our model, usually you have to do some kind of preparation to use it with one of these libraries, like normalizing the features, perhaps transforming them in some way, and using, for example, a PyTorch data loader and dataset class to run a training loop. And so these three things are provided for you or are made convenient. So all of our dataset classes inherit from the PyTorch dataset class. If you're familiar with the Torch Vision libraries, for example, they provide similar functionalities of being able to transform your data. So we thought, why not offer that as well? And so this is an example of doing some of these things. So I'll go over these arguments again for this example. So again, selecting some jets, selecting our particle features and so forth. But I'll emphasize this this option, which is this normalization option. So it's this type of normalization we include, which is basically doing a linear transform of all our input features. And with this normal option, it basically automatically sets them to zero mean and a unit standard deviation, assuming a Gaussian distribution. And we can select which of the features we will actually want to normalize. And so ignoring the mask feature, for example. And one other thing which is pretty common for classification tasks, for example, is to try and one-hot encode the class, the jet type. And so this we can use this transform input and specify an arbitrary function to transform each input every time we try to retrieve it. And so we can specify all those, and also JetNet can do the training and validation splitting for you if you so choose. So we can specify our train and validation data sets, and we can print out these data sets and see everything is specified as we expect. And we can also look at the data samples directly. And just note that indeed the features have been normalized and the jet type has been one-hot encoded. Okay, yeah, that was a pretty quick lightning demo as expected. And we can basically feed this into a data loader and start training. And some more things we can try, if you'd like, is looking at using some of the other data sets provided, like the top tagging or the core gluon data sets. Actually using this in training a machine learning model. We hope to have a tutorial on this soon as well, and using some of the metrics we have for evaluating generative models, for example. Once again, I'll thank you for the organizers, and thank you everyone for listening. I hope there is time for some questions.
Thanks a lot. Very interesting library. So I have one small question. Is the library is called JetNet, and you mentioned several chat-based data sets. But in principle, it seems to me there's nothing really specific about chat. So can this also be used for other data sets where you have just a set of particles that maybe are a bit more distributed in space and not clustered to a chat?
Yeah, exactly. Yeah, that's the goal. It's the hope is to be able to expand it to any type of data sets, including calorimeter showers as well, and full events. As this is just as it's starting out in proof of concept, we started with jet data sets, which are very popular right for machine learning use cases.
Okay, thanks a lot. So currently I don't see any more questions. Feel free to continue as usual on Slack. And with that, I would hand over to Eduardo for some closing words for this year's PyHEP.
Hello, can you hear me?
Yes.
Okay, thanks. Thanks very much. Yes, so I wanted to say a few closing words, as we usually do. So starting with some analytics or some cute plots for you to have, or what the workshop was about in a way. So before I get a few pointers. So starting with the obvious ones, which is something we're always very keen to see, which are the communities and the people who actually register for the workshop. So we have here this big blob of collaborations represented. You can twist your head and see that we have a huge number of collaborations across the globe and various communities represented. Of course, many people participating from the LHC experiments just because of the huge number of collaborators in those experiments. We also see that this actually quite prominent this year. We have a large fraction of what we put on university, so meaning undergrads or even postgrads that are not associated with collaboration by themselves. You see that we have about 400 people there, just as many as the LHC experiments together. So that's quite impressive. It'd be interesting to understand what exactly they could take from the workshop. Okay, we also see, for example, here in terms of gender, that usual thing, whether you look at students or non-students, we have avoided 10-20% of female students, a bit more students rather than non-students with in a collaboration. So this is something we see across the community now, certainly in hydrophysics. So this is no surprise, but you see it very clearly here in this presentation, in this plot. Now, if you go beyond this thing and you try to organize by physics areas, which you try to do here, then you see again at the bottom of the plot, the university, as I mentioned, was over 400 people registered. The LHC is just about the same, and then you have other communities such as astroparticle astronomy, cosmics, high-energy physics, non-LHC, heavy ions computing, instrumentation, neutrinos, and nuclear physics as well, phenomenology. So quite a bit, quite a diverse set of people. And if you look, if you take out the LHC, which are the big experiments, you can see a little bit better. So it's a bit like a zoom of the other plot, and you see that about 60% of registrants are not from the LHC actually, so which is quite good. So if you look like in terms of more collaborations, just to make it in a little summary, in a colorful plots by pie charts by these areas, you can. I'm not going to go through all in detail, but you can see here, for example, for neutrinos, you get some 60 people registered. You have quite a lot of collaborations just by AI. You have a dozen collaborations represented there. Likewise for particle astronomy. Of course, at the top you have the LHC and hydrogen physics on top right. If you go to accelerated physics as well, heavy ions, simulation, nuclear physics as well, I see almost 20 people registered from several collaborations there, like eight or so. This is really nice. Something we are particularly keen on is it's called PyHEP, but we like to see that it's kind of particle physics, quote unquote, in the grants, in a broad perspective. So again, here you can look at the leisure, the economics, cosmology, computing, instrumentation. Again, different collaborations and groups together. So just to finalize a few words in this slide, in this final slide. First of all, thank you very much for your participation. It's really brilliant and to have your participation from across the globe and across such a large number of committees that I just mentioned on the other plots. It was speaking from our side. It has always been great fun to prepare, organize these workshops. We also hope that it was great fun for you to participate in these workshops. So this was actually the end of the first edition already. Sounds like it didn't start that long ago, but this is already the fifth one. As you may know by now, we went into global events, not in person, starting in 2020 for obvious reasons. And that's why we also had such a large number of people being able to attend the workshop, whereas in person you have the usual constraints, especially from talking about students and so on, that they don't have the facility to travel around. And also something that we are very keen on, we have managed to build a nice community around these workshops, and that's something you see from the plot here, where about a third of the people who were attending or registered this year have already attended at least one of the previous PyHEP workshops. So there's a continuity. I was talking during the social time with one student, with one master student. He told me that it was his third participation. So as a student, he was already participating as an undergrad, and now I was also participating as a master student. This is brilliant, and this is really rewarding from our perspective. So big thank you for that. This year, as you know, we try to go beyond the plenary sessions that we have done all the way through these 5 years, meaning we had two slots during the week to do some socializing, and we had 2 slots to try and accommodate everybody at least once, whether you were, say, in US or in Asia, in Europe. We realize we are a bit Europe-centric just because the sheer amount of people actually registering and participating from more or less Central Europe and more or less these zones. Likewise, we also tried something new this year, which is the workshop, again in 2 time zones. So we are very, very keen on receiving any thoughts you might have. In fact, we will probably send out at some point a post-workshop survey, but by all means, if you want to get in touch with us, there's the email on the Windico page. You can always send some thoughts or ask questions, anything. And if you want to stay in touch, so we put together a few links here or in green. So of course, this is the HEP Software Foundation. The PyHEP actually has a working group within the HEP Software Foundation. You have the link there to the working group. We also have meetings every now and then, topical meetings, at the month as we call it. We have our GitHub channel, which is the main way in which we communicate typically, and there's also Twitter, and of course all the GitHub repositories that you can see from for example, from the working group homepage. You have several other links there. So with these words, I would like to thank you all for participating. I'd also like to thank my co-organizers for having run this throughout the week. It's been a fantastic pleasure. It's always great fun to prepare and see these things happening. So thank you again, and I hope you keep in touch, and for anything, just see you maybe around a bit. And with these few words, I would like to close the workshop. So I definitely hope to see many of you around in some occasion or another. I see one of the claps. So thank you very much, everybody. Great fun, and see you next.
Excuse me.
Yeah.
This is Harish. Aren't we going to have a photo this year?
Yeah. Sure. By all means, yes. If you want to take, let's do that. If everybody, anyone who doesn't mind to open the camera, we have not done that, but by all means, please do that. And if you want to take the pictures and send us off, that would be great. Share it on Slack, for example. So,
yeah, sorry guys, I'd like to be, but it says the host has stopped my camera. So, well, I'm François.
What do you mean? Where are you?
I'm François Gutierrez. Let's raise my hand here.
I think Nikolai has to give you co-host rights, maybe.
Okay.
I don't know. It should work.
Okay, it's okay.
For everyone else, it's bizarre.
Never mind.
I haven't tried, but yeah, try to get a few snapshots or anybody for that matter.
It's okay. Never mind. Thanks for the great moment.
You have some pictures or not? Did anybody take some pictures?
Let me work on that.
I actually don't know how to take the snapshots on Zoom.
Yeah, I'm just gonna do a screen grab.
All right.
But let me try and get as many people on my screen as I can at once.
Yeah.
Okay, so okay, there's oops. Sorry, Francois, I think you're now okay, there we go. Okay, so let me try this one more time. Okay, okay, sorry, let me try that once more and then we're good. Just want to take some multiples. Okay, we have some photos, so we can go with that.
Okay.
Yeah, thanks. Yeah, thanks everyone. Also, thank you also to Eduardo specifically, who has done a huge amount of work as he does every year for this workshop. So without his leadership, we definitely wouldn't be here today. So thank you, Eduardo.
Thank you, folks. That was a pleasure. Thank you for helping out quite a lot. All right. So for anybody at CERN, let's have a beer at some point, or any kind of CERN, don't hesitate to contact us, any of us. All right. See you, folks. Bye-bye.
Thank you. Thank you, everyone.
Bye-bye.
Hello. I see there's a few people that forgot to switch off the Zoom.
Exactly.
All right.
Did I stop? I'll at least stop recording.
Yeah.
Okay.
All right.
Cool. Thanks everyone for joining.
Thanks,
Also, Lucas, I was glad to see you were here today. I know that you're doing multiple workshops this week. So
yeah. Cool. But yeah, all that stuff looks really nice. Bye-bye.
Cheers.